Well, I'll just do a little bit of quick housekeeping. Because we have 4 hours set aside, we'll take a break every hour for a little bit. I'm not going to torture people. Don't be over concerned about having your laptops open and typing in. Most of my workshop is really what I call code follow versus code along. Code along is when you open your laptop and you're typing with the person. Code follow is when I show you the code and I walk line by line by line through the code. And then if you have questions about it, I answer. Okay.
So do we get access to the code that you?
Yes. Okay. So a little bit more, give you a little more background here. So I'm part of Google, as you all know. In about a year ago, Google started the process of about how do we make machine learning available to the general software developer. Before that was really just the realm of data scientists. You basically needed a PhD, in statistics, computational theory, and all that. A lot of things have evolved. I'm working in one area, and that's educating through Keras. Okay. Keras is a machine learning framework, but it was designed under general software engineering principles. So it's an OOP framework, object-oriented. It supports design patterns and uses imperative programming. So it's a, sorry, I went cold. There we go. So it's really much easier to get started if you're doing it for the first time to start with Keras. A lot of people will, if they take on a career as machine learning, they will likely migrate to what's called tf.keras, and that is where Keras and TF2O, as you heard, has been built into TensorFlow. But TensorFlow, of course, has the production-grade libraries, the production-grade stuff for the very big, heavy lifting. So Keras is, really good if you're a student or a software engineer and you want to learn how this stuff works. Okay, and then again, everything you learn about it is migratable to tf.keras. There we go. Okay, so I figured you were asking stuff will be available. We have a repo here. I know that's kind of a long name. Okay, so in github.com, Google has, I'm part of GCP, so we have this anchor repo called Google Cloud Platform. It's got all kinds of employee open source repos in there. And I am the Keras idiomatic programmer repo. Okay, if you're curious about idiomatic programmer, it's because we teach machine learning using design patterns. That's idiomatic. Okay? And the slides and handbooks, when you're in that repo, you'll find in ML, there's a subdirectory called ML4ALL. The handbooks are there, the slides aren't there, but they'll be there later sometime today. Okay? The other thing I can tell you, so part of teaching machine learning to software engineers is we've started writing handbooks. As you know, most of the books out there on machine learning are very data science focused. Ours are software engineering focused, and they're shorter. They're not like 300-400 pages each. The book is typically 60 to 80 pages and is on a specific subject, and this workshop actually follows the handbooks. Okay, so we got an early copy of the handbooks available for you guys to look at subject. Okay, so kind of ignore my estimates there. The number of slides we have to cover these 3 handbooks is clearly more than what we covered in 4 hours, so we're going to kind of pick and choose and do a condensed version and see how far we get. This is actually our first trial run at giving the workshop for you. So I'm going to start off talk about models. Okay, I'll talk a little while about neural networks. Okay, then move move on to convolutional neural networks. But at some, yes. Oh, sorry guys, I forgot the on. Okay. And then once we get through convolutional neural networks, we're going to talk about a bit more advanced convolutional neural networks. We'll talk about wide convolutional neural networks, and then use some more advanced ones after that. So that's the first part. Okay. All right. So let's start off with basic types of neural networks that are out there in deep learning. Okay. So of course, Keras is about. Okay, I'll pause for a minute. But you guys can hear me anyways, right? Okay, so I'll keep talking. I think it's just for the recording. Okay. So in Keras, you can build deep neural networks. You can build convolutional neural networks, commonly shortened to CNN, recurrent neural networks, RNNs, and GANs, which are generative adversarial networks. There's actually other types of networks you can build, but those are the four big categories people would use in deep learning. Okay, and just to point out, so DNNs are good for numerical solutions. So people who came from the statistics side and we're doing your linear logistic regressions or your card analysis, if you want to migrate to deep learning, you're going to be working with DNNs. Those who came or want to move into vision, okay, you're going to be working with CNNs. If you are working with time series data, okay. So if you're working with time series data or natural language processing, you're going to be working with RNNs. And if you get into the more advanced or more creative stuff, like style transfer and synthesis and that, you're going to be into the GAN areas. Okay, so just a little helpful hint here. So it's pretty easy to get started. I'm going to assume all of you know Python, or at least a little bit of Python. And once you've installed Python, you have what's called the pip command. Okay, so all the public live modules that you can install are in what's called the PyPy repository out there. And you access them through the command pip. You go pip install the name of that package. And for everything that's in the handbooks, basically you can get with these three installations.
Just quickly, are we using Python 2 or 3 for this?
I do just Python 3. It's going to be Python 2, just to remind you guys, it's deprecated in October. So it's time to get off of it. Okay. So the first thing to think about neural networks is they start with an input layer. You gotta have an input layer, okay? In neural networks, everything takes a number. So in a bit here, we'll get how do you go from what you got into a number, okay? So even if you have text, it becomes a number. If you have speech, eventually it becomes a number. The pictures become numbers. Everything in a neural network is a number. And it starts at your input layer, okay? A lot of you have probably by now heard of the phrase tensors and asked what is a tensor? It's really just a multi-dimensional array of floating point numbers, okay? So a one-dimensional array we call a vector, a two-dimensional a matrix, anything that's more than 2 dimensions is a tensor, okay? And feel free to interrupt me at any time. Okay. So I'm going to start showing you a little bit of code snippets here. Start slow. So once you've installed Keras, and assuming you have either are good at Python or have dabbled in Python, you know that you import modules into your Python file. So you're going to need a line there that says from Keras import, and then the items, the classes, you're going to import from the Keras framework. And I'm going to start it by importing the input class. Okay, and this allows me to define the input to the input layer. In this hypothetical one, I'm going to imagine that I have a 13 element or 13 wide input vector that's going to go into my neural network. So I just tell it their input and I specify the shape. And if you're not familiar with the funny syntax of a comma with nothing after it, that's how you tell Python that that's not an expression. If I went a tuple of just 13, that looks like an expression would evaluate to 13, not to a tuple. Okay, so that's the way that comma just tells it that's not an expression. Okay, there we go. So if you took those two lines and you ran them in a notebook, basically that's the output there. It's going to tell you that's a tensor. It's going to give a default label to it. And it's going to tell you its shape there. Okay? And you can see there's two numbers there, and that first one's a question mark. Okay? We'll get to that in a minute. And the second one, which says 13, says this item is 13 elements long. Okay, and the question mark means is it doesn't know how many you're going to give it. Now, if you think about it, in a neural network, you don't give it just one sample to train with. You might give it 100, 1,000, 10,000. But when you define the model, you don't know ahead of time. That's what the question mark means. It just means that's going to be bound at runtime. Okay, and by default, the data type of all tensors is a floating point number, 32-bit. Okay. Single precision is what I want to say. Okay. Okay. So when we talk about deep neural networks, okay, we're basically talking about something that has an input layer, an output layer, and one or more layers in between they call hidden layers. Okay, and so that's all what a deep neural network means. That it has at least 3 layers. There's at least one layer between the input and the output. It's nothing any more fancy than that. Why we call it a hidden layer, I don't know, other than it's an in-between layer would be just as good of a name. There's nothing hidden or otherwise special about it. Okay? In modern deep neural networks, every node in one layer is connected to every other node in the next layer. Okay? And that's what's called a fully connected neural network. So there's just a simple picture of one. So you can see the red nodes are the input layer, the green ones the output layer. We put one layer in between, so we call it hidden. They're in blue. And you can see at the input how every node is hooked to every single node in the next layer. Okay, and so forth. And if you count it up, for example, the input layer has 3 nodes, the hidden layer has 4. If those 3 nodes are hooked to, every one of those hooked to the other 4, then the number of connections would be 3 times 4, or there are 12 connections between the input and the hidden layer. And that'll become important later when we start talking about the computational complexity of the model. Okay, so when you're programming in Keras, Keras has basically 2 styles of writing models. Okay, one is called the sequential method, and one is called the functional method. And everybody always starts with the sequential method. And really, that just means you're going to layers sequentially flow. It's really easy to think about. Right, the first layer, it flows into the second layer, that flows into the third layer in a nice sequential flow. A functional method means something is not sequential about it. We'll go into that in a minute. Okay, So when you're writing the sequential method, it's going to look something like this. You're from Keras, you're going to import the class sequential. You're going to instantiate it, okay? And then you're going to use the add method to basically add a layer at a time. And my little comments there, they're just comments. I'll later on show you the real syntax. I'm just curious, is everybody here familiar with object-oriented programming and classes and so forth? Okay, good. So don't have to cover that. So this is just pure OOP. Okay, so in the layers approach, which is also the functional API. So in Keras, you're going to hear a lot sequential API, functional API. Sometimes people call the functional API the layers approach as well. I'm a little old school, so I tend to still call it the layers approach. Okay. In that case, from Keras, instead of importing sequential, I import model. Okay. And then I'm going to also, from Keras.layers, import layers. I'm going to do something different now. Okay. Instead of starting in the sequential method, see how I started by instantiating a sequential object and then started adding my layers sequentially to it? In the functional method, I create the layers first, tie them together, and at the end, I create the model object, pulling in the input to the output. Now, we'll go in more detail. But in the functional method where you use model, when you finally instantiate your model, you're going to really have just two arguments. The first argument is that input layer, and the second argument is that output layer. And what you did in between is you decided how to tie everything together in between the input and output, and it does not have to be sequential. Okay. Now, sometimes you might be get a little confused about the difference between the input shape and the input layer, okay? So the number of nodes in the input layer does not have to match the input shape, okay? All right? Because what will happen is every one of those little inputs will get passed to every node in your input layer. Okay, so let's go back to that 13-element array I talked about. That was my input shape. And maybe I'll, if it's not too far back, take right there. So let's say that's my input. Okay, and I'm going to have a neural network, except on the input layer, I'm going to have 10 nodes. Okay, then the number of connections I actually have is 130 connections. I got 13 inputs coming in to 10 nodes. Every one of those inputs is connected to every one of those nodes. Okay. So, so in Keras we have layers are, dense layer is something you have in a fully connected neural network. Okay. So, and that's again like this picture here. So every one of those hidden the input, hidden, and output layers there, those are all called dense layers in Keras. Actually, in machine learning, they're just called dense layers. Okay. So, one type of deep neural network is called a regressor. Okay, a regressor is something that outputs a single value, a real number. Okay, and because it only outputs one number, the output layer is one node. So we might have something that's an input layer of 10 nodes, a hidden layer of 10 nodes, and an output layer of one node. Simple example of a regressor is predicting the house price. One value comes up, the price of the house. That's a regressor or a regression. Okay. So let's go ahead and actually put together our first simple deep neural network in Keras. Okay, so this is going to be a 3-layer fully connected neural network. So again, we're going to import sequential because we're going to use the sequential method. Okay, and then from Keras.layers, we're going to import the dense object. Okay, all right. And so we're going to instantiate the sequential class, and I'm going to add 3 dense layers. A 10 node one for my input, a 10 node one for my output, and a 1 node one for my output layer. Okay. Notice a few other things. Okay, so a dense layer, if one of the arguments is the number of nodes, that's the positional argument, the first argument is required, and then there's some optional arguments, okay? And so the input layer needs to have, you have to specify what's the shape of the input. So you can see I'm doing it there, I say input underscore shape equals that 13 element node. Okay. So let's go ahead and take this exact same example. So that's a sequential version of writing it. So we'll go ahead and write it using the functional method, which I call the layers approach. So in that one, we're going to, we're going to start off by importing the input and the model objects. And I'm going to create an inputs vector. There's my inputs there. And let's continue on. So I'll show a little bit more. Okay, so there's my inputs. There's my dense. So you can see here, when you layers, you tie your layers together. So I'm going to use this syntax here to say this layer, the output of this layer is the input to that layer. So that's how I just tied them together. Okay. The syntax sometimes looks strange to people. Okay. In the layers approach, layer objects are defined to, are also defined to be what's called in Python called a callable. Okay, so this is polymorphism in Python. So if you take an object and you call it as a function, it acts as a function, and that function binds whatever you passed into it, the output of whatever you passed to it as its input. So let's put it all together. Okay. So, see the first line there, we got, again, we defined our inputs. Our next line, okay, so our first layer, we're just going to call it input. Okay, it's 10 nodes. And we're binding into it the input vector. Okay, the output of that is bound into the next one, we call dense 10. We put in input, out comes the hidden layer, and then one more along where we input hidden into a dense layer 1. The output of that is the variable output. Now let's tie it together. It's pretty simple. I want to tie that to that, right? So that's where I get that. So I'll just pause for a minute. Is everybody able to follow along okay? Okay. I guess we're... Do you have a question?
No.
Oh, okay. Okay. Yeah. Okay. So the next thing to think about is what's called activations. Okay. So the output of every layer, okay, goes through what we call an activation function. Without going into the science behind it, we always squash the output into something else, okay? And the thing that does that squashing is an activation function. So think of it this way. If I had, for every layer, I have some result come through it, right? All that stuff goes to nodes, they produce a result. But before instead of just returning results, I return the activation value of that result, which is some other function A that somehow modifies that result. That's all it does. An activation function is just modifying the result coming out of your layer. Okay, and just this important line below, the reason activation functions were added to the neural networks, and they were added a long time ago, is they found it made them learn faster and better. Okay. I'm not going to show you all the activation functions or their histories, only the ones that are important right now. Okay? So in all modern deep neural networks, and including CNNs, okay, the activation functions used all the way up to the output layer, which is a separate issue, are always some form of what's called a rectified linear unit. Okay? The basic one looks like this, and all it does is says any value less than 0, I'm going to clip and just send a 0 through. Any value above 0, I just send the value as is. That's all it is. It can also be expressed by this simple function here. Okay, take the maximum of 0 and the value. So if I have a negative number, the maximum is 0. Otherwise, it's the number you passed it. Okay, so what I didn't show you when I used the dense layer is by default in Keras, when you don't specify an activation function, it's basically what they call, it defaults to a linear activation, meaning there is no activation function. The value just passes straight through as is. Okay, but we want to be a modern neural network, so what we're going to do is we're going to add an activation function after every layer. So this is that same code I wrote before. So here's our first layer, the input layer. So I just do an add activation function. Add another input layer. That's that hidden one. I add my activation function. And remember, this is the sequential method here. So every time I do an add, I'm adding to whatever the last thing I added. So it's nice and simple to write. Yes?
Can you explain again? So when do you choose to use the sequential? When will you use the functional?
Okay. If you're writing a fully connected neural network, okay, and that would generally be when you would write something like you're going to do your own linear regression, logistic regression, or card analysis, or you're working with structured data, you pretty much would always be using a sequential method. Okay, if you're in imaging, okay, and you're just learning how to do computer vision, everybody starts off with the sequential method. Okay, but in production, we've long ago stopped using the sequential method and gone to more advanced architectures. So in the workplace, you really won't be using the sequential method anymore. Yeah. But it's how it's sort of the build-up, how you learn. Okay. So another nice thing about Keras is, so you wrote this, and you're not sure if you made a mistake or not. You're reading the code. Is it really 10, 10, and 1, and are there really activation functions in between? At any time in Keras, you can call the method summary, and it'll just give you a listing of what you've done. Okay, so it shows me I start off with this dense layer. The output shape is, remember, the first column is always, none is the same as a question mark. It doesn't know how many samples I'm going to give you yet. Okay, so it's a placeholder. So its real shape is 10 nodes. Then it goes through a rectified function. You can see the ReLU. That's 10 nodes. Then another dense layer, which is 10 nodes, and its corresponding a rectifier unit. And then finally, the last dense layer is a single node. Okay. I think later I go into how to count parameters, but not right now. Oh. I guess that is the next slide. So let's look back at that. Okay. Again, avoiding going into too much statistics, but if you remember way back in high school or early college, you know, you did some linear algebra and you remember the slope of a line. And there were actually two numbers in there. There was that weight, right, or that x value, and then there was the y offset, okay? So in machine learning, you have the same thing. You have weights, and you have what's equivalent to an offset called a bias, okay? So every node has a bias. So if I have a 10-node layer, I got 10 biases. But my weights are on the connections, not on the nodes. So if I got an input vector 13 long, where every input goes to every node, I got 13 times 10, that's 130. I got 130 connections, so I got 130 weights, but I have 10 biases. So 130 plus 10 is 140. Oops. That's why that's 140. Okay. So I think I covered that. Oh yeah, and just to emphasize, in the neural network, what you're learning are the values for the weights and the biases. Okay. So, Keras kind of gives you different ways of writing things. So, I like to show the differences early on, because what happens is you go to other people's GitHub, you read blogs and so forth, and sometimes the syntax looks strange to you and you can't figure out. Keras is pretty flexible in his syntax and there's different ways of writing things. Okay, so, but once you get used to it, it becomes obvious. Now, let's go back to here. Notice how, okay, activation functions always follow the layer. And so here I just sequentially went layer, then activation function. And the next one, right here, Keras allows you to specify the activation function that will follow your layer in the same instantiation. So you don't anymore here see, you know, the dot add ReLU. I just put it as an argument, keyword argument. Excuse me. Okay. So the next important thing to think about is I put together my model. Really the last step to finish up the model is I'm going to call a method called compile. And compile is going to kind of do what the name sounds like, compile your model. Okay? And if you have any mistakes in your model or things aren't going to bind in that, it'll actually give you an error. Okay? So part of what compile does is that you also specify your optimizer. And again, I'm not going into the science here or exactly what an optimizer is or backward propagation and all that sort of skip. There's plenty of blogs out there to read if you're interested. Okay, but you have to specify an optimizer. And the optimizer is the function that controls the learning of your model. You run some samples through, okay? And on the other end, it compares them to the expected values, and there's some difference. Some are right, some are wrong. The ones that are wrong, we just simply call that the loss. And then something's got to take that loss and figure out how to make adjustments to the weights and the biases in the neural network so that you're going to you get less and less and less loss. And that function is called an optimizer, and there's all kinds of optimizers in neural networks. So when you compile, you specify what loss function and what optimizer you want to use. Okay. So, as I pointed out, the calculation of the error is called the loss, and it can be calculated many different ways. Okay. The most common one people start with is the mean square error, or sometimes just abbreviated to MSE. Okay? So what you want in the optimizer during backward propagation is you want to minimize the loss, and what you're looking for is this phrase called convergence, okay? And what convergence means is you sort of hit a point where you stop improving. You kind of hit that best possible point, you know? You know, in machine learning, you should never expect to get 100% accuracy, or if you are, probably something's wrong. Okay, but let's say the very, very best you're going to get is 99%. You might see during training at first, slowly you get up there, or maybe then it speeds up and makes some big jumps, and then it sort of levels off, 97, then 98, then it's 98.5, and then 98.6, and 98.7, and then smaller, 98.75, and then it's getting smaller and smaller and smaller with each run. That's convergence. Okay? And that's kind of how you know when you're done training. Okay? So here we get, again, show a little line here in Keras. So I'm going to go my model object. After I've defined all those layers, I'm going to call the compile method to compile it. And I'm going to specify what loss function I'm going to use and what optimizer I'm going to use. And at this point, you've defined a model, okay? So let's go a little step further about the output layer, okay? So if the output layer is a sort of a yes or no type of value, true, false, yes or no, is the person going to default on their credit card? Okay? That's kind of what we call a binary classifier. Okay? Then the output node, today we use an activation function. Let's see, that would be the sigmoid activation function, which is going to basically take whatever value comes out of it and squash it between the range of 0 and 1. Okay? And of course, if it's close to 1, that's a, or 1, that's a true. If it's close to 0 or 0, that's a false. Okay, so when we use a, that's also called a logistic classifier. Okay, so when we do a logistic classifier, we're going to take that same model that I showed you. So this model is just going to decide if something is true or false, basically. We're going to make just two changes. So now the activation function on our output is a sigmoid. Okay, and the loss function that works best for a binary classifier is called binary cross entropy, so I'm going to update that. So I've just taken that same little simple example and turned it into a binary classifier. I'm going to check on the code. Okay. So let's take the same thing again, and now we're going to rewrite it using the functional API, called the layers approach. Okay. So let's start with kind of down a little bit. You can see where we created the input, where we created the dense, the input layer, dense 10, tied in the inputs, then the activation, then the next dense layer, then the activation, then the dense layer, finally the output layer, which is an activation, a sigmoid activation. Notice the syntax will always use this variable x. This is very common with Keras programmers. If they use a functional API, but are really writing a sequential flow model, pretty much always will call the inputs, the variable name inputs, will always pretty much call the output either output or outputs, and every layer in between, they just simply reuse the variable x. Okay? So you can see the output here was x, that becomes the input. The output was x, that becomes the input. The output was x, that becomes the input. You'll see that in a lot of code examples. That's all that means. There's really no reason to keep reinventing the variable. It's just a temp variable that's just tying the layers together. It's different though if they start doing something that's non-sequential. Okay, so the next type of a deep neural network is a multiclass classifier. Okay, and that means that you're going to be predicting a category, so it's not yes or no. Okay, so maybe the what breed of dog you have, for example. Okay, so in that case, the output, the activation function for the output is a softmax. Okay, and to just keep it real simple, every node in your output makes an independent prediction. So if I have 10 different classes, okay, and let's say again, we'll just reuse the idea of breeds of dogs. Let's say I have 10 different breeds of dogs. I got 10 nodes in my output, one for each breed. And each one's going to make an independent prediction without the knowledge of the other. Well, if I added all those numbers up, I'm probably not going to get 100% because they're all doing it independent. Someone might say 78, one might say 63, another one might say 2%. So what softmax does is just a formula that takes all these independent numbers and re-squash them so they all add up to 100%. Okay? So, now let's go ahead and take that same neural network and let's now make it a multi-class classifier. In this example, instead of having one node in the output layer, I'm going to assume we got 5 different categories that we're predicting. And so I've changed that to a 5. You can see I've changed the activation to a softmax. And the other thing here is it's pretty common to use Atom, okay, when doing a multi-class classifier. You probably noticed previously I've been using RMSprop. That's generally pretty good if you're doing a regressor or a logistic regression or a binary classifier. Okay, but as you start doing this, you'll start to learn which optimizers are best for which types of problems. I'm just trying to show you the basics. Okay, so we can start moving into the computer vision part here. Okay, so let's just think about what an image is. It's actually, if you're not familiar with image data, it's really planes of data. They're matrices, okay? So let's start with a grayscale image, okay? It would look, under the covers, the data on your file would look something like a matrix, okay? So as you see, lines, or you think about rows across your images, there are rows in the data that form to that image, and then the value in every one of those locations is a pixel. Okay, and it's just saying how strong or weak that value is. So values in a grayscale image are 1 byte integers, so they're between 0 and 255. So if I had a 255 here, this pixel would be fully white. Have a 0 here, that pixel would be fully black. It's really that simple. Okay, but so let's say I wanted to take my deep neural network and have it classify grayscale images. Okay, what's the problem here? It's not a 1D vector. Remember, so first I said they take numbers, but they also take a vector of numbers, and this is the wrong shape. Okay, so we'll fix that with a technique called flattening. Okay. This is probably about the only place I'll talk about minced. It's kind of outdated, but it's good, easy here to talk about it. So mints are these images that are 28 by 28 pixels. So that's really that shape, but 28 this wide, 28 that wide. And I got to change it into a 1D vector. Okay, and 28 by 28 is 784 pixels. That means I need an input vector, 1D 784, And the way we do it is you take the first row, you start there, you take the next row, and you put it behind, concatenate it behind it, take the next one, concatenate it behind it. Real simple, that's what flattening is. You don't have to do that because Keras will do it for you. So let's take that pretty much same model. Let's kind of just modify it a little bit for mints. If you ran this model, you'd probably easily get 95%, maybe even better. It's really easy to do mints. Okay, so here's what I've done. I've now made, my input shape is really 28 by 28. It's not a 1D vector anymore, okay? But my first layer is a flattened layer. That will change that to 784, okay? Then I put it into my first hidden layer, which in this case is 512. I do a ReLU, I give it another hidden layer of 512, do a ReLU. Mints predicts digits 0 through 9, so that's 10 nodes. I give it 10 nodes in the sigmoid activation function. Again, it's multi-class, so I use categorical cross entropy, going to use atom on that. Okay, so let's go ahead, and again, as I mentioned before, so you've written this model, and you're not 100% certain that you wrote it right, and you want to look inside what's in there and double check. So again, just remind you, just execute the summary method. So here it kind of verifies for you what you did. So your first layer is a flattened layer. You're supposed to get 784. There you go, 784, you did it right. The next one is a dense layer of 512, next one 512. You know, the ReLUs, of course, are tied to it. So the output of the ReLU is always the same number of outputs as the layer that's going through it. Okay, it's just squashing the values in that output. It's not changing the number of outputs. Okay, and then finally, my final dense layer is 10. Not going too much into it yet, but you know, I've already alluded to learning weights and biases, and those add up. Even though this is a very simple model, that's already 700,000 weights and biases, or almost. And that's what you're going to learn. You're going to have to learn, this model's got to learn the right value for every one of these 700,000. Aren't you happy you don't do that by hand and deep learning does it for you? Okay. So the next thing to do, to think about, is overfitting. Okay, so you're training, and I already kind of alluded to convergence, where you sort of level off, you're not going to get any better. Well, it turns out that if you keep training your neural network past that point, you might actually go the opposite direction. Now, your accuracy on your training data may actually continue to improve, but the model may actually get worse used on what we call real-world data. And what can happen is you can start causing the model to try to perfectly fit your training data. Okay? And if it fits it too perfectly, then it's just learned those samples. It hasn't learned to, quote, generalize to samples it's never seen. Okay, and that's called overfitting. And we'll get more into that, but it's easy to recognize it when you're training. Okay, so in training, you do passes over your data. We call them epochs. And every time you do an epoch, you get an estimate of the current accuracy on the training data. But you'll also then take some other data, typically called validation data, that you didn't train on, that you run tests on and check its accuracy. Okay? If you start seeing the training accuracy continue to go up, but the validation accuracy is going down, you've just overfitted. It's really easy to spot. Okay. Now, there are other ways to prevent overfitting so that you can continue to train more epochs without snapping in the samples too tightly to the neural network. The general phrase for it is regularization. There's many different types, but the easiest one to start with is what's called dropout. Dropout is kind of like forgetting. The reason I don't perfectly fit the model to the data is that I keep forgetting things. And so it's like you purposely put some forgetting into it. Okay, this kind of keeps it a little bit loose and generalized. Okay, that's done with a layer called dropout. So you can see that when I'm importing these different types of layers, this time I've added dropout. Okay. What dropout does is you give it a percentage. In this case, 0.5 needs 50%, and it randomly drops values being passed through. And drop values just means that it sends a 0 through. So you got to think of a neural network. When something goes through a layer to another layer, that's a signal. Okay, and by setting to 0, that's the same as no signal goes through. Okay, so randomly, every time something comes through, some random number, and it's not always the same ones, will just send a no signal through. And so nothing is perfectly learned. Okay. So here was just an example of that. I took a snippet of that model there. So you have that 2 hidden layers, and I just said, I want to randomly forget information 50% of the time after the first layer and then after the second layer. Okay, gonna check the time. Okay, we'll go about another 10 minutes. We'll take a break. So let's start really more or less into the imaging side of this, the convolutional neural networks. Okay. All really a convolutional neural network is bolting on the front end. You know, right up to now, this is what we've talked about, right? So CNN just is this sort of front-end preprocessor you put in front of a deep neural network. Okay? So another way to think of it is the CNN, the front end, does what's called feature learning from your image data. Okay, what are the features that are important in your image data? That becomes the input vector to the back end, which is going to do the classification learning. So it's sort of a 2-step stage. Okay. Okay, so you could ask, well, can't we just continue doing this with a deep neural network like I showed with NIMS that had that 784 input vector? Well, yeah, for tiny little images, but you know, today images are kind of big, you know, like 1 megabyte. And do you really want to have an input an input vector that is 1 million pixels long? It'll take you forever to learn. Okay, here's an example. So let's say I had a 1 million pixel input vector, and my input layer was 1,024 nodes. Well, 1 million times 1,024 is a billion connections. Right there on my very first layer, I have to learn 1 billion values. Yeah, it'd take forever. Okay, so let's kind of start with how do we take what would seem like a huge problem and make it a manageable problem. Okay, well, the first thing is that we don't really need all that resolution to recognize what's in that image. Okay, so let's take a typical image that might be 1024 by 1024, is we can downsample or resize it into a smaller image. Okay, most modern neural network CNNs work around this range, 224, 229, 230. Okay, so the first step is to take that big image and get it down to this smaller size. So we're already working with a lot less pixel data. So I think you can see it here. If I had a 10 by 24 pixels, that's basically would have been 1 billion weights. But if I downsample it to 24 by 224, I'm down to 154 million width. So I'm getting better. Okay. All right. So as I said, CNN convolutional layers, your front end to your neural network. So it's going to transform the images sort of from what we call this high dimensional pixel space to something that is substantially lower dimensionality and that is feature based. Okay. And it's going to be that substantially lower dimensionality of features, not pixels, that ends up getting inputted as a input vector to the deep neural network, and then the front end, so the convolutional front end really becomes the front end between your image data and your deep neural network. Yes?
Is that downsampling something that happens in the input vector, or do you?
You pre-downsample it.
Yeah, okay.
You can build it into your, automatically build it into your model too.
A lot of work.
You could just do a max pooling, start off with a max pooling layer.
Sure.
And that would effectively accomplish it for you.
Sure.
So what do we mean by feature detection? Okay. Well, it means having this concept of filters that looks at the image data and recognizes, just say, shapes or lines or something, okay, more than just a pixel. So usually it's a progression. You start with recognizing really coarse items, and as you move through layers, they start assembling those coarse items into more and more detail, at the end some detail. So I just kind of used the eye as an example. So early convolutional layers might be recognizing some edges and patches, okay? So those are sort of and those become contours that recognizes, those get assembled, and it's this sort of shapely line here, and this circle here, and this circle here with a shade in it, right? Okay? And then later layers learn the spatial relationship, and the next thing they know, they recognize this. Okay, so that's what convolutional layers are learning. They're learning features, not images, and these, not pixels, and these features are basically the contours, the shapes, and the spatial relationships. Okay. So, a convolutional layer performs the task of, as I said, the feature detection within an image. Okay. So the way they do it is they do it with filters. Okay, and these are, you say they're n by m matrices of values. So it's just another matrix. And in there are certain values in there that are used when they're overlaid on your image data to see, did I detect that? Did I detect a line? Did I detect a curve? Did I check sort of a color change? Okay. Now we don't pre-write these filters. I actually was an imaging scientist for 20 years before deep learning, worked for Sharp Corporation in Japan, and we hand wrote these filters. Okay, so we did computer vision before deep learning. And it was extremely expensive, and it took an entire room of PhD people to do it. Convolutional neural networks, they learn those filters for us. Okay, so those filters sort of start off uninitialized. Their weights, just like in a neural network, and during training, it's going to learn the weights of those filters. Okay. So yeah, I kind of already told you prior what it was like before neural network. As imaging scientists, we had to design these by hand. Okay. So in a convolutional layer, one of the things you're going to do, we'll show it shortly, when you specify a convolutional layer, is there's another argument now, or two more arguments now, and that is what is the size of your filter? Okay, that's the matrix size, height by width, and the number of them. So there's some conventions out there. Most of the time, filters are 3 by 3 or 5 by 5. And really, the most common is 3 by 3. So when you're first starting and you're uncertain, just make it a 3 by 3 filter and you'll probably be okay. All right? The number of filters can vary when you're working still with small models, not huge models. They're typically multiples of 16. So 16, 32, 64. Those are the types of numbers you see most often out there. So let's kind of see what a filter does. Okay. So as I mentioned, so this filter is that matrix. You're trying to learn the weights inside of it. And once the filter is learned, really what's happening is it's being dragged across your image and then the next row, right? Okay. And it's then comparing the filter to what's there in the image and deciding how strong of a match between my filter and what I found at that spot in the image. And it makes a feature map in the same spatial relationship where the filter was that indicates how strong of a signal, how strong of a match between the filter and what I found there. Okay. Now, the rate at which it moves across there is called a stride. Okay. I'm not going to go too much into strides at the moment, but it just says, do kind of like, do I move 1 pixel at a time, or do I move 2 pixels at a time? So you can see if I had a 3 by 3 filter and I moved what's called a stride of 1, I'd have a lot of overlap. So first I covered 3 pixels this way, right? Move the filter 1 pixel. I'm overlapping 2 pixels here. Okay. If my stride was 2, I'd be only overlapping 1 pixel. If my stride was 3, I'd have no overlap. So another thing you can see here in the blue, so each filter is what you're learning, and it produces a feature map. So that's what you're learning.
Can you pause for a sec? I'm sorry.
Sure.
Can you repeat how do you design the filter itself?
How do I get what?
How do you actually design the filter? Like,
Oh, you don't design the filters. You design the size of the filters. Like you might say, in this case, they're going to be 3 by 3.
Yeah.
And the number of filters, I'm going to have 64 filters. Okay? And then the neural network learns what's in the filters. So presumably if I said 64, each one of those filters will try to learn something different. But you really can't predict ahead of time what they're going to learn or which filter learns which feature. That's what the magic of deep neural network. If they're not learning enough, then you need more filters, right? And you can say, well, I'll just put in 1,000,000 filters, I'll learn everything. Well, if it's way more than your need, do you really want to spend a month training your model instead of a few hours? So, yes.
If you examine the filters that it does create, do they actually look like edge
In
detection
some cases,
filters,
yes.
or-
You can look at filters. There's plenty of blogs if you blog out on there, but especially a lot of analysis on how filters are learned have been done on the CFAR 100 data set. This is sort of a warm-up data set for the big competitions, and everybody practices on it, and then everybody who writes research papers and peer reviewed practices on it before they do the big test, okay? And so you'll see a lot of analysis has been done looking at the different layers and at the feature maps from the CFAR 100 data set, and you can start seeing the progression of seeing more and more of actual features that we visually recognize. I think it's a good time to take a 10-minute break. There we go. So we'll just pick up again on the idea of filters and strides. So, you know, there are some trade-offs here. The more filters you have, you know, the more you can learn, but it also means more data. That is, your model is bigger, it's more computationally complex, is going to take more memory, is going to take more time to learn. Okay? So increasing filters increases the data. The strides, remember I said with that overlap, the bigger it is, the less overlap. So obviously the bigger the stride, the less data that you're going to need, or the smaller the model is, the less computationally complex. Okay? But the trade-off is it might not be able to learn what you're trying to learn. So you're trying to find that right balance. Okay? Okay. So another concept is pooling. Okay? So we've talked about convolutional layers. It's common between convolutional layers to put in what's called a pooling layer. To simplify it, a pooling layer is like a downsampling. It takes those feature maps that you've generated from those learned filters that might be pretty big and downsamples them into a smaller size. Okay? Kind of like a compression. A typical pooling layer will reduce the size of those feature maps, usually 75% to 90%. And that's a way of, again, controlling the computational complexity of your model. Okay? So, yeah, so we've covered that. So let's just kind of visually look at what pooling looks like. So let's say, for example, that convolutional layer we showed earlier generated this sequence of feature maps. Remember, every feature map is going to be the same size. Okay? Let's say we had 32 filters. We would have 32 feature maps. What the pooling would do is then shrink every one of these feature maps into what's called a pooled feature map. So they're a little smaller. So in your pooling, you specify how much you want to pool it by. Usually the way it's done is you create this little window, okay, like a 2 by 2. And in max pooling, which is the most common thing, is you just take the highest value of those 4 bytes and you replace it with 1. So that by itself would be a 75% reduction. Okay. So finally, okay, so that's our front end. And let's say we've done this many layers: convolutional pool, convolutional pool, convolutional pool. Okay. But at the very end of our CNN front end, we still have those pooled maps, right? And we're going to go now into the back end, which is our deep neural network, which takes a 1D vector. So we're going to need to flatten them. Okay, so let's go ahead and just show some code for that. Okay, so let's start with the simple stuff. So we're going to introduce 2 new types of layers, a convolutional 2D. Okay, all right. And that just means the 2D just refers to the fact that the feature maps are 2D feature maps. They're matrices, height by width, okay? And a max pooling layer, okay? So let's start here. We're going to go ahead and create a sequential object. And then we'll add our very first layer. So this time it's got a little bit more options here. So that's our conv2, that's our convolutional layer. We're going to say it has 16 filters. Okay. The size of those filters, what we talked about earlier, are going to be a 3 by 3. Okay. In this one, the stride, how fast we move across rows, and same thing, how fast we move downward is 2 by 2. I'm going to just throw this in right now. You know, in the early days, people would try non-square values like a filter of 3 by 4 or a 5 by 3 or a stride of 1 by 2. That's all gone by the wayside. They're always the same. So nobody would. So your strides up and down are always the same, and your filters height and width are always the same. So a lot of times people don't say anymore a filter 3 by 3. They just say 3. They don't say stride 2 by 2. They just say a stride of 2. Okay? Yes?
So you have filter of 3 by 3.
Yeah?
You want to move
2 pixels at a time.
yeah, but why is it 2 by 2?
I'll go into that in a little bit later. Okay, but the question she's asking is how you pick that stride, and we'll go in, we'll build up to that. Okay, padding it's a little early to get into, but for your sake, when you're first starting, it's always best to set padding equal to the same. Okay, and it really involves about the filter and the stride. Okay, so let's say at a stride 2 by 2, you can see when you get to the end, let's say that last 3 pixels, and then you moved over to, well, filter's actually only on 1 row, and 2 columns of the filter are in outer space, out of image. Okay, padding says is how do I treat when I get to the edges that out of image space. Okay. Same just says whatever that last row was, that last column or last row, just duplicate the values. Okay, and then finally my input shape here. So this is basically a gray image that's 128 by 128 by 1 channel. Okay, and we'll go into that. I think I go into that. If I don't, RGB images, which is what you're normally going to work with, there are really 3 matrices. One matrix is the R plane, or the red color, then the green plane, and then the blue plane. So in gray, you got 1 matrix. RGB, you got 3 matrices. So if we were RGB, that 1 would be a 3. Okay. So the next step is, as I mentioned when we did the deep neural network, we always now take the outputs of these layers and send them through a rectified linear unit. That's the same for convolutional layers. So the next line here is a ReLU. Now I want to downsample those feature maps, so I'm going to do a max pooling. A 2 by 2 with strides 2 by 2 basically gives me a 75% reduction in the size of them. Okay, and again, when I'm reducing, that just means with later layers I don't have to learn as many weights. It's less computationally complex. But if I downsample them too much, maybe I've lost too much information to learn anything in the first place. So it's really finding that right amount. Okay, and then finally flatten. So those few lines right there basically implemented that step there. Okay, so now we're ready to attach our front end to the say DNN classifier. Okay, so what do we got here is, so we took that front end. Okay, we've just flattened it. Now we can pass it to a dense layer because it takes a 1D vector. In this case, I'm going to say it has 512 nodes. Okay, then put it through a rectified linear unit. I'll just say activation function. Hypothetically, let's say you're trying to recognize hand sign letters. The hand sign letter A, B, C. There's 26 letters, so I got 26 categories. Because I am trying to classify categories, I want to use a softmax activation. So remember, every node, those 26 nodes on that output layer, each of them is going to make an independent prediction, and I want to squash them all together so that they add up to 100%. And then obviously the output node with the highest percent is the one we say, oh, it's the letter C. Okay. And then finally, I'm going to compile it. So I'll go into a little bit more into softmax, or what we mean by that is you can't think of a neural network as exactly knowing something. So let's say something is the letter A. The node for the letter A, we want it to put out the highest possible signal comparison to the other 25 nodes. But those other 25 nodes are still going to put out some signal. Okay? And the idea with softmax is we're trying to figure out which node really not only is the strongest signal, but on a probability. I don't want to tell you, 14.6. This 14.6 doesn't mean nothing to you. I want to tell you it was the strongest signal, and it's a 97% probability that it's the right answer. Because that's what you get from a softmax. You get the probability of it being the right answer.
Why do we use the rectified linear there?
It just seems through research gives the most reliable results. I mean, years ago they used a hyperbolic tangent, and that was pretty good. And researchers just experimented with different activation units, and in the end, the ReLU was the one that sort of, in the research community, they sort of universally decided on is the very best.
So is it sort of just like not throwing out too much information in the data?
I don't really know about, all the activation units, for the most part, are trying to squash the range of values and clip them somewhere. So, in a hyperbolic tangent, everything's going to be squashed between -1 and 1, and it's going to have that S curve, right? The moment you move away from 0, it's going to either quickly move to a 1 or quickly move to a -1, okay? And then in a ReLU, it kind of goes the other way. We're not going to squash the positive range. If it's 14, we're going to send 14. If it's 0.2, we're going to send 0.2. But if it goes below 0, we'll just cut it off. We clip it to 0. There's other variations of it that are used, but that's the basic one. Okay. Oh, yeah. Okay. So let's take that same model I just used and do a model.summary again. Again, always encourage when you're starting off, or even if you're pretty good and something's going wrong, do a summary of your model. Look what you actually did. So I just here help you read this. So that first layer, that convolutional 2D layer there, okay. Now you can see instead of, before we only had one number here, now I got 3 numbers. You're asking, oh, what's this? Okay, well those first 2 numbers are the size of the outputted feature maps, in this case 64 by 64, okay? And that's the number of filters, okay? That goes through a rectifier unit. Of course, it's going to always be the same, right? So you should see 64 by 64, 16 filters. Now we go max pooling. So we're going to downsample this, right? So when we're done downsampling, those filters are now only 32 by 32. They're not 64 by 64 anymore. So they're 75% less total data. Okay. Then we're going to take these 32 by 32 matrices, 16 of them, and flatten them. That gives us 16,384 elements in our input vector to the dense neural network backend. Okay, that first layer has 512 nodes. Then you look at this. Whoa, where did that number come from? What is that? Over 8 million. Well, that's because the number of weights is, remember, when you get to a deep neural network, every input is connected to every node. So that's 16,384 times 512 plus every node. This is of the nodes, has a bias, plus another 512. That's how you get that number. Okay, and you can see a similar thing here. Going down to the last, here we are outputting 512 values to the final layer, which is 26 nodes. So all 500 of those 12 values are hooked to every one of those 26 nodes. So 512 times 26 plus 26 biases for the 26 output nodes gives us that number. And so the total computational complexity of this model is 8 million. Okay, this is the kind of problem. That's actually a fairly high number for how simple this model is. And later on, we'll start showing how convolutional neural networks have evolved to greatly reduce that number. Okay, so let's take that same model that we wrote. And I like writing it this way because you can see it's easier for me to put it on the screen. I'm going to use the functional API, my layers approach. So I start off by declaring the inputs, right? Okay. And then layer by layer by layer. Here I use the word layer instead of X. Okay. But as you can see, I just put the inputs into the first one. Start with that, right? And then I start attaching the layers to each other. You know, the input goes to there. That's the output. The output goes to the next one, and so forth. Finally, I get to the output layer, and then I put it all together. Inputs, output. Okay. So VGGs is sort of like the father of sequential convolutional neural networks. They were designed by the visual geometry group at Oxford. They really became well known in 2014. Probably by now everybody's heard of the annual ImageNet contest. It was going on long before 2014, where people in signal processing went to this big contest to see whose algorithm was really the best at recognizing objects and images. Okay, and actually it wasn't until 2012 the first time anybody ever came to this contest with a convolutional neural network. Okay, so this design, VGG, which is generally where most people start nowadays, won the 2004, or in parts of the contest it won in 2014. And really, it certainly didn't invent the idea of having convolutional layers or connecting them together in a sequential mode. What they came up with, how to group them. Okay? And basically, the way VGGs work is you have these groups of two convolutional layers that have the same number of filters. Then you pool. The next convolutional group doubles the number of filters. Then you pool, and you keep applying that each time. Squeeze the size of the feature maps down, but then on the next group, double or explode out the number of the filters. And that's a VGG. Okay, so let's go ahead and write a real simple VGG real fast. Okay, so I'm going to have two blocks, right? So we'll just do a sequential. It is a sequential model. So instantiate sequential. So my first group, I'm going to have two convolutional layers, right? Okay, notice that there's no max pooling in between them. The max pooling is only after the group. Okay. By the way, I'm just going to tell you, so strides one, how would I say that? That's called a strided convolution. That basically retains the most amount of information possible. Okay. So there's my input. I'm going to reduce it by 75%. Now I go to my second group, see how it's really exactly the same, except I've doubled the number of my filters. Okay, so that's I guess you would call it a 4-layer VGG. Okay, and I kind of removed a few lines here. And then finally, I just flatten that and send it to some dense layers. Okay. So let's kind of look at a VGG16. This is one of the more popular versions, okay, of it. All right. So if you are end up taking, you know, in college, something to do with convolutional neural networks, early on they'll have you write a VGG16. There's plenty of model zoos out there where you can just get a templated one, okay? Now, I kind of like to stress using good programming practices. So if you notice back here, these are kind of repetitive sequences, right? Except for this number here. Why not make them a procedure? Okay, that's what's good about Keras. It is an OOP, it's a imperative programming language, NOOP, so I can use my good software practices and actually use them. So I just made a function block here, call it a convolutional block, where I'm just going to send in the number of layers and the number of filters. In this case, what we're doing, not going into too much, but in a VG16, they also have a stem that starts a little differently, so we'll ignore that. But then here I'm going to have 2 convolutional layers of 128. The next group's going to have 3 convolutional layers, but I'm doubling the number of blocks and so forth. So in just a short sequence of code, instead of writing it all like this, just using good coding practice, I can snap together VG16 real fast. Oh, they do take RGB images. The whole VGG class was optimized for images that are 224 by 24, obviously color images. So here's an example where that input shape is 3 channels instead of 1 channel. Okay, so the next thing after a VGG is what's called residual convolutional networks. And this now gets you into modern stuff, okay? So this starts off about 2015 when ResNet came out of Microsoft Research, basically took first place in this competition. And actually, that's incorrect. ResNext by Microsoft did that, so I got the wrong term here. This was a Google one. Okay, so typo. Okay. It used a different layer-to-layer connection. We're not sequential anymore. Okay, all right. So it introduced this new concept. So VGGs had sort of a block pattern. So that's a design pattern. They came up with a new block pattern and a new layer connection. And they referred to the blocks themselves as residual blocks instead of convolutional blocks, and the new layer pattern as identity connection. Okay. What is really good about it, and I'll just jump ahead, is that it found to have the same learning capability as VGGs, these sequential convolutional blocks, but a substantial reduction in the number of parameters. That means they were much less computationally expensive to train. You could train them much faster and get the same accuracy. Okay. So a residual block in, say, a ResNet 34, which is sort of your standard off-the-shelf one, consists of blocks of 2 identical convolutional layers, okay, like you saw in VGG, but without a pooling layer, okay. And then each block has what's called an identity link, which basically is I'll show a picture in a minute, a parallel link from the input to the residual block to its output. So you have this, let me see. Should be a picture. Yeah, okay. So here it kind of looks a little bit like a VGG. I got 2 parallel convolutional layers, same number of filters. I got this sequential flow coming through. But I have this additional link here. It's kind of like a bypass link, okay, that sends the same output here and adds it back in. And they call this an identity just because it's exactly equal to the input. You add the input into the output here. And that's called an identity link. And we'll show you how to code that. It's really simple. But what they found, both in research and then in competition and in practices, is that it allowed neural networks to be built with deeper layers without degradation and performance. And what's important here is up at the time this came out, the conclusion in the sort of research world was the only way to increase accuracy was to add more layers. Okay? The problem with adding more layers is two things. It took longer to learn, right? More complex. And two, I kind of want to skip the technical behind it, but there was this problem called the vanishing gradient. Okay? The deeper and deeper you went, because of the way hardware worked and multiplications of tiny, tiny numbers, you started losing resolution, and basically your numbers really went to zero. That's the vanishing gradient. So you could only go so deep in layers, and this solved the problem. Okay, so let's just take, this is what a residual block looks like. It's really easy to read. So you remember I've been using sort of this notation where the output is, the input is X, the output is X, and so forth, keep tying it back and forth, right? So imagine there's something up here where its output was X. So that's my input coming in. I want to remember that input. So I'm just going to call it shortcut. You could call it bypass. Then I just built my sequential block, right? So there's that X. Goes into the convolutional 2D array loop, the next convolutional 2D array loop. But now I'm going to use this add operator method, okay, to say to add this shortcut into X. And that becomes my new X. And this line by itself implements this matrix addition operation in a residual block. So it's really easy to do in Keras. It was really messy in before TensorFlow 2.0 and TensorFlow. Okay. So as I said, unlike VGGs, there's no pooling layer between the groups that would reduce the size of feature maps. Okay, let me see. The shape is. Okay, yeah, we need to do the strided issue. Okay. Here's the thing. When these residual blocks, because I don't pool the data and get things smaller, and the next little block I want to double the size, okay, when I double the output size and the input gets added to it, that input has to match the size. But it's half the size right now, okay? So I need to add a convolutional layer between residual blocks to basically get the input into the correct shape that the output of the next block is for me to do my identity link. So the way it works in ResNext is after you do a residual block is then you have this convolutional layer that reshapes it for the next block sequence. And so here's an example code. Again, I like to use good coding practices. So here we just use reusable procedures. So a residual block, as you saw, there's some layer coming in, right? That's your input. There's so many filters for this. So 2 convolutional layers of those filters. Add the shortcut in, okay? The convolutional block, similar types of arguments. The input coming in, how many filters. There you go. You got your 2 convolutional blocks. Each of them return X, which is just the output of the block. So now when you write code, hopefully, and you start writing these bigger neural networks, you don't write these big, long copy and paste lines. In fact, it used to really annoy me when I would read other people's examples like 2 years ago that were written mostly by data scientists who did not come up the software side, but the statistics side, how bad programming practices they followed back then. And stuff used to just be written in a very scripted, long, sequential manner. It was really difficult to read. Used to pull my hair out. Okay. So, another thing that changed in ResNet was how it did flattening and pooling at the very end. So you remember we've talked about on the convolutional front end, the very last thing you have is some number of feature maps, and they got to be pooled and then flattened. So pooling reduced the amount of data and then flattened in a 1D vector. Okay, so they brought in the idea of global averaging pooling. Okay, this is kind of a poor man's front end to pooling. Instead of having something like a window 2x2 and taking the max value, it does more of an an averaging over an entire plane. Okay, it's an approximation, but it turns out if you got lots of feature maps coming in, lots of filters, doing approximation, which is a tremendously amount faster, will give you just as much capability as if you had done it the long way. So they introduced global average pooling. And what they found in a ResNet, unlike a VGG, is that if you did enough residual blocks, you will learn all of the final features. There's no more feature learning, so you only need an output layer, one output layer. So suddenly, what you saw in those other pictures is we had multiple dense layers that continue to learn the classification. Okay? In modern neural networks, all of them now, that last layer, that back end, is almost all the time one single output layer. So classification now moved. Not only did we have feature learning in the front end, but now classification learning, for the most part, has moved into the front end. Okay. So, as I pointed out to you, I'm going to read that. Okay. So VGG16 wins in 2014. It's got 16 layers. It's got 138 million parameters. Next year, ResNet wins. Okay, it was a ResNet 34. That's only 34 layers. Gets more accuracy and only has 21 million parameters. That's less than 1/6, almost 1/7 as small. So you can see that change in layer structure significantly changed how convolutional neural networks are written. Let me look at the time. Okay. And probably what I'm going to do is just go a little bit further in advanced neural networks, and then we'll go into the data engineering. Okay. All right. So a bottleneck residual block. So after ResNet 34, they came out with ResNet 50. And this is when they started exploring the idea of factorizing. Okay, you notice how we had those filters 3x3, 3x3? Okay, so the question is, can I refactor those filters, getting even less computational complexity, but what's called representational equivalence? That is, can I design this so that these are less additions and multiplications, but the output here is the same as the unfactored version? So this was the first factorization that they introduced. So let's go. It was part of their research showing you could factorize this and have representational equivalence. And nowadays, everything is factorized. So they took this sequence here, the ResNet 34, the two 3 by 3, 3 by 3. So I'm not going to go into science. Just tell you what they did. And they made it a 1 by 1, 3 by 3, 1 by 1. Okay. This greatly reduced, well, this reduced the total size by 4. So that means moving data through here moves 4 times faster. Okay? But what's represented here is representationally equivalent to the same unfactored one. It's not exactly the same, but they say it will learn the same, that there is no loss of information when it comes to learning. That's what's meant in deep learning when they say representational equivalence. So I'll just quickly show you how to write a bottleneck residual block, which reduced that by 4. Okay. So before you saw we had 2 convolutional layers, 3 by 3. Now we have a 1 by 1, 3 by 3. And the next one bumps it by 4 times the number of filters. Okay. And so you can just write it in that tiny little bit of code. So that whole little picture there, right here, is just those few lines of code. A few years ago, it would have been a tremendous number of lines of code. Okay. Another thing that started to appear around the same time is this concept of batch normalization. Okay. And I'm going to skip the statistics behind it. Okay. But one of the problems I tell you about is that as you add layers, you become more and more exposed to the concept of vanishing gradient. And what it really means is there's a point at which your hardware cannot represent a tiny floating point number. Okay. All these numbers, if you haven't noticed yet, are numbers between 0 and 1. And if you multiply 2 numbers, both less than 1, you get an even smaller number. And you go to the next layer and you multiply that even smaller number by another number less than 1. You get an even smaller number. Go far enough and suddenly the precision of your hardware is just not there. 0. Okay? So you still have this problem even though with the residual block we can now go a whole bunch of deep layers far further than the sequential model. At some point you still hit the problem. Okay? And they solved it with a technique called batch normalization. And it's just something they do at each layer that's part of the activation function. Okay? Another great thing about batch normalization, it allowed us to use half precision. Okay? Half precision are floating point numbers that are only 16 bits long, not 32. If you think about your hardware, doing a 32-bit operation times a 32-bit operation takes so much amount of time. But if both are half the size, in theory, that operation 4 of those operations can happen in the same amount of time. So you're now moving your data 4 times as fast through. But again, you would have had that vanishing gradient. Batch normalization protected us from that. Suddenly we could run this stuff now on 16-bit hardware. 4 times the speed up. Okay, but you need to add in the batch normalization. Okay, so a general rule of thumb when you're writing convolutional neural networks is after every layer or group before your activation function, you'll add this new layer called batch normalization. So as you can see, I had my 2D convolution, batch norm, then the activation function. Here I have my dense layer, my rectifier. Oh, I say I put it in a different order. I should change that to be consistent. My batch normalization. When batch normalization first came out, there was a debate in the community. Does it go before or after the Prelude? There were pretty much 2 different camps on it. But the convention today is they always put it before. And we'll probably take a break here in a minute. I'll cover a little bit about wide neural networks, and then we're going to probably end on
about models, not go any further, and pick up after the break on data engineering. Okay. So up to now, we've focused on networks with deeper layers, block layers, and shortcuts. So, in 2014, Google came up with Inception v1, and Microsoft came in v1, GoogleNet. In 2015, ResNext by Microsoft Research. Okay, and then Inception v2. And all of these introduce some new ideas, okay, about having wide convolutional layers. Okay, and you might ask, oh, what's a wide convolution? Well, think of a dense layer, that's nodes, right? If I add more nodes, they get wider, right? Okay, so how do you make a convolutional layer wider? Well, let's now sort of break it up, those feature maps, and then sort of have lots of little mini convolutions in a convolutional layer and spread it out. So before what you saw, if we went down here, here's your input, right? And you went through some single convolution that had some singular filter size, okay, like a 3x3. And now we're going to take this data and we're going to actually, in parallel, put it through multiple at the same time in parallel, and then concatenate it together. Okay. Okay. And so what happens is this is called a branch and concatenate technique. Everybody kind of heard sort of Inception really kicked off things big time. Okay. And back in 2016, 17, everybody talked about Inception, big revolution in imaging. And it was this, one of the big things it introduced was this branch and concatenate technique. And I might cover one or two more slides. But so, you want to know how to write that? Well, it turns out to be pretty easy to write, right? Okay, so we're going to say X is our input from the previous layer, right? So we're going to have these three separate branch convolutions. Let's look at the picture again. So we got a max pooling layer, three convolutional layers, a 1x1, a 3x3, and a 5x5, right? So there's my max pooling, there's my 1x1, my 3x3, my 5x5, right? We show in this picture X branches and goes into every one of them, right? So all of them just take X, 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 but if they're outputs, I give a unique name. X1, X2, X3, X4, those are the branches. Concatenate them all together. So I just wrote an Inception module in those few lines. All right, probably a good time to take another 10-minute break. Hopefully I'm not moving you guys too fast now. Yeah.
if you don't mind. So.
I just want to get back to something.
Oh, sure.
Okay, what's up?
In section.
All right, well, I'll start up again. So we're going to skip the rest of sort of the advanced model stuff so we have enough time to go into other things. But I'm just going to quickly show you some slides, not really say anything, just where you get an idea of what's in the handbooks. So here, Inception V1 explored even more factorization and what they called dimensionality reduction. Again, it was just a short code sequence to show how to do it. Sort of this, Inception V1 also kind of introduced other types of groups. The idea that convolutional neural networks now start with what's called a STEM group. All modern convolutional models have a STEM group. They also explored the idea of auxiliary classifiers. Those were in favor for a while, but they've kind of dropped out of favor. That's sort of the block architecture of an Inception V1. Okay, ResNet went with the idea, how do they call it? Not just having convolutions that went wide, but the residual links and all that go wide. So they had a totally different idea. What you saw earlier was you took all the feature maps and you split them across your parallel convolution. Okay, here they split up the feature maps. Okay, so they could make the layer even wider, but if you made in a parallel layer 32 convolutions, you divided your feature maps up by 32. One 32th went here, one went there, and then they did the concatenate, and then the identity link. Okay. That's kind of a picture. Again, you'll see all this in the handbooks in a lot of detail. There's some code. We'll talk a little bit about what are STEM groups now and what's called a strided convolution. V2 went into more factorization. The idea is they figured out how to get rid of 5 by 5 filters altogether. They're very computationally expensive, and they show that 5x5s can be replaced by 3x3s, and I think you get a reduction by 33%. So you're just that much incrementally faster, and you have still representational equivalence. A lot of research in the 215, 216 time frame was on factorization. Okay, and finally we got to V4, where you can see this is the actual stem group. Everything before you start the convolutional blocks. Look how much stuff is in the stem group. This is a little more on pre-stem work, how things are padded. One of the problems is let's say you've defined and optimized a neural network for images are 224 by 224, and they're suddenly being fed 230 by 230. That's called pre-stemming. Okay, so the handbook goes into that, how that's handled. Goes into more detail representational equivalently. And then what are called dense nets. Okay, and it's just another way of reusing feature maps that go well beyond the original identity links. In a dense net or a densely connected convolutional neural network, you saw reuse from one layer to another. Here, the output feature maps of every layer are shared with every other future layer. So it's densely reused. Just more details there. And again, there's plenty of code sequences in the handbooks, how to write it. It's all done, either procedurally or in an OOP style. Okay, exception was yet another Google one. Came in 2017. They took factorization even further and introduced new types of convolutions. Okay, so that's what those are all about. And sort of a new approach to the overall architecture of a convolutional neural network. Then, starting about 2017, we started thinking about, now we want to deploy these models on mobile devices. You're constrained by memory, chip performance, and all that. How can we make these models even smaller? Things like quantization and pruning. So that's covered in there. Okay, so that would be the rest of that. So now we'll go to the next section, which is our data engineering. And this is everything that's sort of in front of the model. Okay, so you kind of get a sense how computer vision models are designed. But in the end, it comes down to the data, right? So we need to collect the data and assemble it. We need to do some kind of preparation or engineering to the data. We're probably going to want to do some what's called data augmentation. And then I kind of wrap up on this concept called data curation. How do you finalize your data set, curate it? In data collection, we have a lot of things we need to consider, okay? And the quality of my classification is really going to be dependent on both the quantity, how much data I have, and the distribution within that. So here are some things, problems people typically ran into with an image data set that didn't perform well. One, they had just too few images, okay? Or maybe they had too few images of a specific label. So let's say you were doing cats and dogs, but 90% of your images were cats, and only 10% were dogs. Okay, you know what that model is going to learn? Everything's a cat. It will. You'll get 90% accuracy. You think you're doing great. The 10% you'll fail on is dogs, because they'll always come out as cat. You didn't learn anything. Okay, insufficient variance in the perspective. Okay. The problem with the original deep neural networks is because you were learning pixels, it was important the position of those pixels. Okay, so if you think of a cat, if I shifted the cat over in that image, deep neural networks weren't going to work. The great thing about convolutional layers is they can learn those spatial relationships independent of where they are in the picture. But you got to give enough examples for it to learn that spatial relationship. So that's the variation in perspective, like angle and zoom. And then you're deploying this in the real world. If your data collection came all under one lighting condition, and you deploy in the real world, it's a different or great variance of lighting conditions, it may also fail. So let's look at too few images. Okay, and so that's the features associated with each class. So we want to have enough images to learn the features associated with each class. And we want the distribution of those features across each. Here are things we need to look at. We may have too few features associated with a label, or too little of a distribution, or not enough variance in the feature of each label. Okay. So let's take this example. We have samples of fruits of different colors with and without stems. Okay. So here are things we need to consider. Okay, we have apples, oranges, and pears. Okay, and we know that they're kind of similar in shape, while bananas are different in shape. Okay, so we want to have enough distribution. It'd be really easy to tell the difference between an apple, orange, and a pear from a banana just by the shape. Okay, but between an apple, orange, and pear, it's going to be harder. Okay, we know oranges are fairly consistent in color, while apples and bananas can have a range of colors. For apples and pears, some of them can have stems and some of them can't. So we got to think of all those things and make sure our data set is representative of all of that variance if we're really going to learn the difference. Okay. So another example of too few images overall is we may not really consider how the model would be used in real life. So here, I trained it on perfectly looking fruit. These are great fruit examples. Oh, I'm going to recognize all this fruit. Then I put up a website, take a picture, I'll tell you what fruit it is. And people start loading stuff that looks like this. Of course they're going to do this. I don't recognize anything. It looks nothing like that. So you got to consider the environment your model is going to be used in, and the images that you're actually going to see in your training data never has to be representative. So in this case, I used humorously examples of fruit that are partially rotten or even partially prepared, like sliced and so forth. They're still fruit. We recognize that. We know that's an orange, but your model may not. Okay. So let's start with some best practices about I'm going out there, collect images for my data set. Okay. So generally we say each label, and so a label, which can also be called a class, is that unique thing you want to learn. So that's an apple would be like a label. A pear would be like a label. Okay. We generally say you want at least 1,000 images. Okay. Okay. Okay, and let's say what you want to learn comes in different colors. Okay, we'd like to really say that at least 10% of the labels are that color, but that might be enough. So let's take an apple. Let's say hypothetically there are only red ones and green ones. Okay, as long as one of those colors has 10%, okay, that color, it's still okay that the rest have 90% of the other color. It will learn those two colors. It's when we start going below that percentage that we tend not to learn. Okay, a lot of times, okay, sometimes you have secondary features that we don't always associate with it. Okay, so let's take this apple. little leaf there. We don't usually think about that leaf. The presence of that leaf could cause a model down the road, if it wasn't trained for it, to fail to classify that as an apple. Okay, so those secondary features that don't necessarily occur quite frequently, we generally suggest that 5% of your training data has those features. Okay, and then as I had humorously noticed, if the items you're learning have some kind of age progression, whether it's fruit slowly rots, or people, we get older, or children who get bigger and grow up start looking like adults, we need some kind of distribution of that progression. We usually say it should be at least 20%. Okay, another helpful thing that many times improves overall accuracy is trying to train the model with everything else is not what you're trying to train it for. So if you're trying to train it for 100 different things, let's say 100 different types of fruit, just keep sticking with the fruit, then create 101 class, call it not any, and throw all kinds of things in it that aren't fruits. An airplane, a car, a barking dog, it doesn't matter. Okay, but we find that in general, adding a not any class can help increase accuracy and recognition of what you do want to recognize. Okay, so another problem, of course, is what we call an unbalanced data set. That means any one class just simply has too few images in it. We made a note earlier on that, the idea like cats and dogs, if 90% of the images are cats and 10% are dogs, the only thing you're going to learn is what a cat is. Okay? So what we generally say in these multi-class ones is that there's kind of two ways of looking at it. First, you want to take a mean of the representation. Okay, so one data set has 300, one has 400, one has 350. The mean is just the average. Okay, any one class, we generally never want it to fall under 20% of the mean. Okay, and these are like bottom numbers that usually you need to do better. Okay, and then again, the same thing, if you take the class with the most number of labels and the least number, not the number of labels, I mean the label with the most number of images and the label with the least number, that least number should at least be 10% as big as the one is the most. Once you go below that level, you become what we say is unbalanced and you won't be able to learn. You need sufficient variance and perspective. Okay, so and one of the reasons we want to do this is we don't want to fit the model to the data. If your data is so perfect, the model will learn, in some sense, that perfection. And that's what it's going to expect when you do recognition, and it's going to fail. Okay, you'll get 98, 99, 100% accuracy on training. You've done a wonderful job. You deploy it and it's like 10% and you ask what happened. Well, you overfitted it. Best way to, I talked earlier about using dropout in the model is one way of dealing with it. The other way of dealing with it in conjunction is with the data itself, adding enough variance in the data so it can generalize and not try to pick perfectly. So here's an example where I've done some rotation of the images here. Okay, so this one is kind of like a perfect shot. And this is actually the exact same image. I didn't take another picture. I just did a little trick that changes perspective. Okay, and we'll go into that a little bit later in what's called data augmentation, where you can take your existing pictures and change things about them to add more data without actually going out there and taking that picture. So let's talk a little bit about spatial relationships. So As we talked about in our convolutional layers, we have feature maps, right? So we have so many feature maps, okay? Every one of those feature maps is detecting some kind of feature. You know, it might start up really coarse, like a line, and get refined to an eyebrow and later to an eye. But they're learning them in the same area as this guy, meaning whatever it learns here versus this feature, which is a different feature, is learned here. They're the same location in the image. Okay, so that spatial relationship between features is maintained in your feature maps. That's what allows us to start recognizing things, like your face, okay? If we didn't learn spatial relationships, we might think an eye here and an eye down there is a pair of eyes. Well, you see that on the picture, and you go, that's not a pair of eyes. I don't know what that is, right? But two eyes kind of more or less like this. That's a pair of eyes. So that's a spatial relationship. And that is, this technique allows to learn that is a pair of eyes, not some weird drawing like this. Also, the idea that sort of a nose forms a triangle type of a spatial relationship, so forth. Okay. So another thing is having insufficient lighting. Okay. Okay, and so you got to think about where you're going to use your application. I mean, in some cases, you might be okay. Let's say you're in a factory and there's a conveyor belt and the lighting is always the same. Okay, well, then that lighting's good enough to train your model, right? Because that's the only place it's going to be used. Okay, so you got to consider where you're going to use the model. Is it going to be natural light daytime? Natural light dusk. If it's indoor, is it going to be well lighted? Is it going to be dimmed? Okay, so the next step here is now you feel you got enough images and enough variance in the images and enough balance. So now you got to assemble them. How do I put them together for a model? I just don't just throw them there. Okay, so generally, we have this sort of hierarchical concept. Okay, so we have what's called an image data set. That's going to hold all our images. And then we kind of break it down, next level down abstractly as we think about it as the top level labels. So cats or dogs. Okay, but then if we want to go to more refined classifications, then we'd break that down. Okay, for cats, here are our breeds. For dogs, here are our breeds. So we've kind of followed this hierarchy in classification. Now, and I'll just point out, because everything I've showed you today, it's usually how you're shown, is you're only shown image classification at a single hierarchy. Is it a cat or is it a dog? Or even if they show it as a breed, type a breed of dog or type a breed of cat, you don't get shown how first at one hierarchy it says, that's a dog, and then goes into further classification. Now that I know it's a dog, what breed of dog is. So if that's the type of image classification you have, you need to group or categorize your data following that type of hierarchy. Because you have to tell it the grouping and hierarchical relationships of the images. So yeah, a couple things about the number of images. Again, the general recommendation is 1,000 images of each class. Some things to think about here, okay? If this is for play or for school or for personal use, nobody cares about the copyright. But think about it. If you're at a business and they're going to sell something and you're using somebody else's copyright images, even though you're not displaying the image because you used the image in development of your model and you're making money off of it, under the copyright law, you violated their copyright. Okay. Okay. The other thing people sometimes wonder is, how perfect do my images labeling of my images need to be, let's say I hired somebody, I got 20,000 images, and they need to go through every one of them and mark cat, dog, something, okay? And people get tired, sometimes they don't know better, sometimes the images might be confusing, and so there's some mistakes, okay? And later on when I talk about curated data sets, talk about those that are highly accurate. But in general, most data sets have some error rate in them, okay? And what we find statistically for deep learning, as long as that error rate is less than 4%, we're pretty much okay. So you don't have to have it absolutely perfect. So another issue would be the background diversity. So you got the item you want to recognize in your image. The background is everything else. Okay? So when I showed you earlier the fruit, I had a nice solid white background. So that's an easy one, not a big of a problem. But the real life is you'll be outside taking pictures, inside taking pictures, blah, 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 blah. Okay. You want to make sure that your classifier or your feature detectors learn the background features, because they're features too, aren't part of the recognition. You want, in a sense, to unlearn the background. So you have to have enough diversity within the same label for it to learn, oh, those other items aren't what make that label. Okay, a really classic example was a paper published in 2016, and there was this classifier that was built to recognize whether something was a wolf or a husky. Okay, and what happened is that the data set for wolves were taken during the winter. Okay, and so in every single shot of a wolf, the background was snow, and the model had high accuracy. Okay, and nobody thought about it. And then when they tried to say for real, in the wild, every time a picture of a dog had snow in it, it said wolf, and somebody said, "Oh, what's going on?" And it's because inadvertently learned snow as being a wolf than the wolf itself. Okay, so how do you lay it out? The most common way, since you generally store images as files, is we use a directory structure. Okay, so using that same one, fix this. So here at the top level, we have sort of a parent directory. That's our cats and dogs. Then let's say we have two classes. One's cats, one's dogs. Those are separate subdirectories. And then we put the images inside those subdirectories. Fix that. Okay. All right. If we were even more hierarchical, oh, no, that's a different one here. Okay. This is an alternative approach. So in some frameworks and some methodologies, you leave it up to the framework to split your data into train and test. In a bit, I'll go into what that means. And in other methodologies, you make that decision about in the data set itself. So if you're deciding for the training what images are training and what is test, then usually the convention is you add this sort of intermediate directory structure. So under the parent one, you now have train and another one called test. And then under them, each of them, is where you split into subdirectories that are your classes and add the corresponding images. Okay. Yeah, and then here's an example where I talked earlier about your data, if your data is actually hierarchical. So it's not really cats and dogs, but breeds of cats and dogs. So at the first level down, I'm going to break it in the high level hierarchy, cats, and then dogs. And then within cats, break it down into breeds. Within dogs, break it down into breeds. And once I get to those root leaf subdirectories, that's where I put the images. Okay. Another common convention, okay, is to not necessarily care where the images are stored or how they're stored, but use a CSV file to list every image and say what its label is. So typically the CSV file, every row is going to be a label and a location. So that in this case, those images can be anywhere. Okay, and here on the right side, I give an example where they're actually remote files. We refer to them by their URL. You could even embed the image data itself into the CSV file. And we see those as well. In fact, the local one and the embedded one you see quite frequently on Kaggle competitions. Another common format for specifying data sets has been JSON. It's really the same as CSV, but in a JSON syntax. So every, think of it as a list. Those are the outer brackets. List is a row of objects, right? And every object has two fields in it. One is a label, one is the location of the image. Another very common layout, particularly for image data, which can consume a lot of space once you start talking about millions of images or even more. Okay, the most effective, both in space and performance, is the HDF5 file system. It kind of came out of the big data area. Okay, that stands for a hierarchical data format. It is still considered the most efficient for both storing and accessing large amounts of what they call multi-dimensional data. Tensors are multi-dimensional because they're three dimensions or more. Okay, there's vast amount of data today stored in HDF5. We don't even think about the real satellite data, the real sonar data, the real MRI data. Okay, all that's considered multi-dimensional data. We store in HDF5. So once you start getting into those types of areas, you're going to have to know this file format and the tools for accessing it. Let's give you just a quick look at HDF5. At the top level, basically, you create groups. You can assign attributes to those groups. Within those groups, you can create subgroups and assign them attributes. And within a group, you can create blocks of data. Okay, so here's a very simple example how I just mapped that cats and dogs. I made two groups. The attribute I called, I got a problem there. That one says label, that one says name. They both should say label, typo, but their label is cats and dogs, right? And then within them I made subgroups. Those are the breeds: Persian, Siamese, Poodle, Beagle. And within those subgroups, I put in the data set. Okay. Another common thing you might find is your data set, when you call it, actually comes fully in memory. This is typical when you use what I call the curated data sets of the ML frameworks. Okay, so if you use Keras, there is a module called data sets where you can get sort of pre-built data sets like mints, CFAR10, CFAR100, a whole collection of ready-to-go data sets. Well, when you call that entire data set is brought into memory. It's not on file, it's not on disk, it's not referenced through a JSON file, it's not in HDF5 format. It's going to look something like this. It's going to return in what they typically refer to as X and Y, X being the data, Y being the label, and the underscore train meaning this is for training, and underscore test, this is your test data. And they're going to be matrices, you know, that are multi-dimensional arrays of matrices. Okay, so that's pretty much data collection. So data engineering. So as I point out, you just don't drop an image into a neural network. So there are some pre-processing steps that need to be done to images before you can input them in for training or subsequently for inference. First, you need to read that image into raw pixel data. You need to fit that image into the input vector of the neural network. You're going to do some conversion of the pixel data. And then finally, you're going to need to do some splitting of the data set. This amount of the data used for training, this amount of data used for test and or validation. Okay? So we're going to kind of touch on the different ways of doing this using OpenCV or conversely PIL or Keras. My preference is OpenCV, but it's really up to you which way you want to do it. So we'll start with the PIL library. PIL is really native to Python. So a lot of Python users will use PIL for their image preprocessing. I just find it's not as flexible or as fast as OpenCV, but it's perfectly fine. So I just start off, that's how you install it. So you do a pip install pillow, and that'll bring in the module. Okay. As before, shown you before, to use it, you're going to do a import statement. So from PIL, so from the module PIL, I'm going to import the class image. Okay, and here's a simple invocation of reading that image in. Okay, so that image is being read off disk. Now you got to remember, when we store images on disk, we store them in a compressed format. That's not raw pixel data. JPEG is a type of compression. PNG is a type of compression. Those different image formats, they have different names because of the compression algorithm they're using. They all start with a raw pixel. And raw pixel, I mean, is when I refer to those color planes, and each pixel is in its sequence position. Okay, so that's fully expanded out and considered raw. Then I figure out some way, some algorithm that compresses that data down. So that call will read it into memory and uncompress it into a raw pixel format. Yes, convolutional neural networks do not work off compressed image data, they work off of raw image data. So, but the reality is I'm not reading one image, I'm reading a whole bunch of images. So let's kind of go back to our picture here. Okay, one further back. All right, cats and dogs. So I may want to first go into the directory cats and then read every image in that directory and label that as a cat, right? And then go into the directory dogs, read every image in there and label that as a dog. So I wrote a little code snippet here. So this is just a little function called load images where you give it a directory. So that directory could have been cats. It's going to create a list of images. Those have been read from disk, now in raw pixel format. So the scanner just simply scans that subdirectory for all the files. From this simple case, we're going to assume every file in that subdirectory is an image. So we're going to walk through that list of files. That's that for file in files. And we're just going to append to our list reading in that image. So you can see that line here, image.open. So we're just going to read in every single file in this directory and append it to this list and just return now that list of read in images. They're now in memory. They're all in raw pixel format. Okay, now let's kind of make this a little more advanced. So that was kind of just one directory. Let's say, now let's think about the parent directory, cats and dogs. And what I really want to do is I want to go into each subdirectory, read all its images as a group, and give it a label. So in this one, I just called it load directory. So I'm going to create a dictionary called classes, because I'm going to want to map my classes to my labels. Here's another important thing about neural networks. So your images are cats and dogs, okay? Neural networks work only on numbers. It's not going to output the word cat. It's not going to output the word dog. It's going to output a number, 0. 0 means cat. 1 means dog. So I have to know the mapping of what the neural network is, numerical number it assigns to your human label. Okay, so that's what classes is. And then the data set is just going to be my list of images by class. So using that same idea, I'm going to go to the parent directory, cats and dogs, scan for the subdirectory. So that's cats. Another one is dogs. So I'll go through that twice. Okay. Here I'm just now improving the code, making sure that everything I'm looking at, okay, is, if it's not a directory, skip it, because nowadays a lot of times when you get a third-party data set, guess what's right underneath that parent root? A license file. You don't want to treat that license file as, oh, that's a class, so that's just a quick check. Okay, but the name of that subdirectory, cats, becomes my class name, and this number of sets I have in my data set just indicates the number that's going to be assigned that label. Okay, and in machine learning, we always start labels, progression labels, starting with 0. Okay, so this first time through, data set is empty. That answer is 0. Next time around the loop, it's going to be one data set in there, so it's going to return 1. So cats will get 0, dogs will get 1. And then here, I just call that little load images routine. So now I've just got everything into memory. Okay, let's take a small example. What happens if, for example, I had like a CSV file or that JSON file, and it had a location of the image, and it's not on my disk? It's really easy to open a file on my disk, but how do I open a file if it's on a remote site? So with PIL, this is basically, well, first you're going to import the requests module that allows you to do HTTP operations in Python. The format that it comes into, that is going to come in there, I need to map into what's called a bytes.io format. So I'm going to import that module. But it really becomes this. I got that URL to that image. I'm going to go request.get. That's going to give me a response object. Embedded inside that response object is my image data. That's the .content. But it's in a base64 encoding. And so I'm going to use bytes.io to get it as a byte stream. And then can get read right into that object. Okay. So another thing you might need to do is channel conversion. Okay. Channel conversion is matching up the number of planes in your image to what your neural network's going to take. So let's say you design your neural network for black and white images, and you got some of your training images are color, you're going to have to change them into black and white, right? Or vice versa. You train it for color, but a few of your images are black and white, got to convert them to color. There are other cases I probably don't show here. PNG images, they're 4 planes. Red, green, blue, alpha channel. People always ask me, what's an alpha channel? That's not a color. No, it's not a color. That's your transparency channels. You know how PNGs, you can have that transparent part in the background you can't do in JPEGs. That's a fourth channel. That's called an alpha channel. So if I load a PNG image into a 3-channel neural network, I need to drop that fourth channel. Okay. Oh, yeah, there I go ahead and I talk about it. Got a little ahead of myself. Okay, so here's just some simple code in PIL for doing the channel conversion. So when you read image.open in Perl, it actually, when it returns to you is an actual image object, a PIL image object, and it comes with methods. So hypothetically, if I had one channel, meaning black and white, I can call the method convert, and this argument, this big capital L here, says make it a grayscale image. If it's, say, presuming defaults to 3 channels, then I'll do the same thing, but I use RGB, and that'll give me the 3 channels. Otherwise, that load image file that we wrote earlier would look exactly the same. Okay, another thing you need to do, resizing. So we've talked several times now how your convolutional neural network is going to have a certain input size or input shape. I think there'd be better ways here, say it. And so your images that you're going to use for training need to match that input shape. Maybe they already do. But let's just say your data set actually has a mix of shapes. That's not so unusual, right? You might get them from different sources. And so we need to resize them all into the same shape. Okay? So in this case, for example, I'm going to say let's say my input shape is 64 by 128. We've already handled the, yes?
So all of this, like over here, so it's all happening in pixels, right?
Yes, yeah.
Everything is happening in
Pixels.
Even the size, like resizing is happening in pixels.
Right, in raw pixels. We might get to in a little bit is in PIL, that image object is not a NumPy array. There's a final step where we got to make it a NumPy array. Where in OpenCV, you're operating on a NumPy array. But I need to reshape it. So let's say my input shape is 3 channels, and every plane or in the channel, the RGB is 64 by 128. Remember, we've already handled the channel conversion, so it's just this part. So we need to resize every image to 64 by 128. So we're going to use the resize method, okay, to do that. So somewhere in here I must have said shape. Yeah, so shape would have came in as 64 128 in this simple example. I deleted some lines for brevity. I'm going to, before I append the image in, I've read it in, I'm now going to resize it to this shape. The only important thing here, there are different what are called interpolation algorithms when you reshape, because effectively you're moving pixels around or you're shrinking it or expanding it. So you got to approximate. If you make something bigger, you got to approximate what would be there, because there wasn't something there. And if you make something smaller, you got to approximate what something smaller as closely resembles what was once bigger, okay? So when you're generally, in most cases, in neural networks, your images are big, your neural network takes a much smaller image, you're downsampling. The algorithm in PIL that works when you're downsampling best is the anti-alias algorithm. Okay. And then, finally at this point, okay, in Python, all neural networks today, no matter what framework you're using, the input is a NumPy multi-dimensional array. Okay, so NumPy is a high-performance scientific library for big arrays. Okay, I won't go into it too much. Python, the way it manages the heap, Well, it gives you great flexibility and can do great things. It's horrific if you want a long, giant array of continuous memory and treat it as continuous memory. Okay? But the worst thing you could do with Python. So the native list representation is just horrible for this purpose. So NumPy is a package written in C, down at the bare metal, that gives you high performance access. So it completely represents the data on the heap, totally different. Okay, and so we use that package for our arrays than the list built into Python. Okay, but you'll bring in that package, and with those images that I said read in, you'll use the NumPy dot as array. That method converts things into the NumPy array representation. So here is just a very simple thing. Again, that same thing. I skip all those lines, but this time instead of returning that list of images, I return the NumPy conversion of that list of images. Now, instead of being a Python list of images, it is a NumPy multi-dimensional array. Okay, so let's try to repeat the same things again, this time with OpenCV. Okay, this is my popular one. Okay, but again, everybody chooses, so that's how you install. Okay, so the first step, of course, is I got to read in the image. So this time we're going to import the module CB2. That's what it's called. Okay, and then to read it, the method is IMRead. So that's all I got to do there. That's kind of like when we did the image.open in PIL. That's exactly the same. And by default, it will automatically read it in as an RGB image. So if it's a grayscale, it will convert it to RGB. If it's a PNG, it will drop the alpha channel, so forth. Okay. If you need to do channel conversion, okay, you can do that at the time you read it in. You don't have to do it as a separate step. So there is a keyword or optional argument here, and that is the what you want to read it in as. So IMRead underscore grayscale reads it in as a one-channel image. Color reads it as a RGB image. And there's a whole bunch of different other ways you could read it in, but almost always this is how you're going to read it. Reading from a remote location, pretty much very similar. Here's that request.get, given that URL, right? You get a response object, right? An HTTP response object. Inside that response object is your image, but it's in a 64-base encoding. You decode it, and that byte stream you can just put right into the method IMDecode, and it'll read it right in. Okay, resizing pretty much has a method. Turns out to be the same name, right? Resize. There's an easy one. Okay, the interpolation algorithm. The inter area is the same as in OpenCV as the anti-aliasing algorithm in PIL. Different names. It's the same algorithm. Okay, so we're just going to go ahead and take that one load images and rewrite it. Looks like I got some kind of typo there. Check that out. Using OpenCV, so we have a subdirectory, the number of channels and the shape. We're going to make this list, right? We scan there, that's the same for every file in there. Okay, we check the number of channels. We either read it in this way or that way. Okay. And remember, this is actually a NumPy array now, okay? And because it's a NumPy array, well, first then we do our resize, but because it's a NumPy array, I can just append it in here. I don't have to convert it, okay? And then now I got, instead of having a list in PIL of PIL objects, so I got to convert the PIL objects to a list of NumPy arrays, and then that list of NumPy arrays to a NumPy array of NumPy arrays. I just have to convert the list. So again, it's faster. I always find OpenCV to be faster. Okay. At this point, you got all your data in raw pixel format. It's all in very fast, efficient memory, NumPy format. Is it ready for your convolutional neural network? No. Okay. And the reason is we always want to import or input numbers between 0 and 1. Okay, we're not going too much because this has a lot to do with statistics, is we'll learn faster. Okay, so just think about the simplest algorithm out there. There's two basic ways of doing it. One's called normalization, one's called standardization. Normalization is just a linear squashing. So integer, since images are 1 byte per pixel, okay, that's between 0 and 255. I just need to squash 0 and 255 between 0 and 1. So just divide my integer value by 255. I'm going to get some number between 0 and 1. Okay? And there we go. Remember with that OpenCV call, this now is a NumPy multi-dimensional array of each image that's in a NumPy format. NumPy has overloaded, it uses polymorphism on all the mathematical operations. So while this in other contexts wouldn't make much sense, this division, because this is actually a class object, this has been overloaded or redefined, will apply this operation to every element in this multi-dimensional array. But it'll do it very fast and quick because it's been written at the bare metal level. Okay. Here's a kind of note. Most of the time you won't encounter this, but you might work with what are called high dynamic range images. Okay. That's not going to be your regular phone stuff or camera stuff. It's really high professional stuff. In that case, instead of 1 byte or 8 bits per pixel, you have 2 bytes or 16 bits. So the range is not 0 through 255, but 0 through 135. I just like to remind people that if you're a double byte, then you need to divide it by that number to get between 0 and 1. So you have to kind of pay attention if you're working with specialty images, what's really inside the image. Okay. Most people have found that while it's only a mild improvement, you get better training results if instead of trying to put it between 0 and 1, if you map it between -1 and 1. And therefore, in principle, half your data is centered at 0. So half your data is above 0, but under 1, and half your data is below 0, but above -1. And so this operation, again, this is all polymorphism, and NumPy will automatically do that for you. Okay. Standardization takes a little bit more computation, but statistically, it's a lot better. Okay, so standardization will squash your numbers again, okay, but not in a linear fashion. It will still center on 0. That is, half your values will be above 0 and half your values below 0. But the spread isn't -1 and 1. It's 1 standard deviation plus 1 standard deviation, 1 minus standard deviation. That gives you what's called a normal distribution, okay, of your pixel data. We have found that mapping your data into that type of distribution, again, improves the time it takes. It shortens the time it takes to learn. But sometimes we still do normalization what people have found is if you're working with grayscale images, okay, doing the quick and dirty normalization seems to work just fine. But the moment you get the color images, you're much better off with standardization. So here's a quick thing with standardization. Again, with NumPy, all this is a high-performance math statistics library. Okay, so it's all built in. This method will figure out the standard deviation on that entire set of data. This will figure it out, the mean on it. All these operations are overloaded. Technically, your standard deviation could be 0. You don't want to do a divide by 0. We always add this plus epsilon on the denominator. It's always set to tiny, just a really incredible tiny amount, just to avoid that rare case you could ever divide by 0. Other means of standard deviation. I'm going to check the time. Actually, why don't we go ahead and take a break? 3:38, because then I can plan how to use up the remaining hour. All right, guys, I'll get started again. So, cover a few more things. So, one of the things when working with the NumPy package, it does all its operations in double precision float. That's float 64. And if you remember earlier, I said the larger that float number is, precision, the longer time it's going to take to do the dot matrix multiplies or adds. So we always try to remind people that when you're all done, to basically convert your data type back into a single precision, or in some cases, if your hardware supports it, okay, into half precision. But you can do that with the as type method and then convert it into the appropriate data type. Okay, so we'll talk real briefly about how to do the Keras has a lot of this stuff built in. You might just find it easier to use Keras' built-in system than writing by hand. It's just writing by hand, you have more flexibility. Okay. So in Keras, they have this class called the image data generator, okay? And that data generator is actually a multi-purpose class. It does a whole bunch of things, okay? But its primary purpose is to create a generator, and that's a Python generator, okay, for feeding batches into the neural network during training. And I'm only going to cover a few of the pre-processing functions here, but they're the ones that we've already been covering, such as resizing, or rescale, which is a form of normalization, setting data type, and various other types of standardization. Okay, and basically, when you use the image data generator, it's really two sets. Okay, first you instantiate or create the object, and when you do that, you're going to specify the type of normalization or standardization you're going to use on the pixel data. Okay. And then two, let's see what these images are presumed to either be in memory as NumPy tensors and already resized if you use the flow one, or, okay, that's what the point was. This object is then used later with two different methods in Keras. One's called flow, that's reading from in memory. Your data is already in memory, so you already need it to have it in the right size. Or reading it from disk. And that's the flow from directory. And if you use that version, then you can specify as you read it from disk what the size of the images are. Okay, so let's go ahead and start with a pretty simple one here. Okay, so here in this case, I'm going to instantiate a generator. It's going to be my data generator. And I'm going to tell it to rescale. Basically, I'm saying divide by 255. So that's just saying when it actually performs the operation on the data, it will normalize that pixel data, squeezing those values between 0 and 255 to be between 0 and 1. So that's just sort of an all-in-one. Okay. There are other means of doing it. If I wanted, remember when I talked about between -1 and 1 and center everything as 0? If you use this option, it does that. If you wanted to do standardization instead, then you would use this option. Okay. So another thing you would do in the data generator is you can tell it what the data type is going to be. Again, it's just like NumPy by default, it would default to float 64. Nobody uses float 64. You know, so you're going to either use float 32 or float 16. Now, I'll warn you about float 16. You may think that's exciting using it. Most commonplace hardware isn't built for float 16, so we'd have to emulate it. It would actually take longer. So it has to have native half precision support in it. All the high-end GPU cards from the video support float 16, but your laptop running a CPU, no, it doesn't. Okay. So here's just a simple way of showing it. So you saw how I created that data generator earlier, right up here. So I just, So I instantiated a data gen as an image data generator. Now I'm ready to use it. Okay. So I'm going to create a feeder. That's going to be something that feeds into my neural network. Okay. So one way of doing it is I could do it from a directory. So I could go flow from directory. I give it the root of a directory. So that could be that cats and dogs one example I showed you. Okay. And then the target size. Okay. So this is going to be as I'm actually feeding the neural network. And it gets a batch. It'll go to this data set here. Okay. It knows that type of directory layout, that subdirectory structure it expects. So it'll grab some out of the cat subdirectory, some out of the dog subdirectory. It'll know the correct labels. It'll automatically resize them. It'll change it to a NumPy array, and it will do that standardization. So sort of all in one. And then finally, because that is a generator, and I'll go more into it later, when you train the model, you're going to use the fit or fit generator method. So if you're using everything in memory, you would use the fit method. But if you're using a generator, because you have memory constraints, you would use the fit generator method. But you're going to give it the feeder, the number of times you're going to take your entire training set and pass it through. And that's what an epoch is, if you're not familiar with that. So let's say I have 100,000 images, and I'm going to run those 100,000 images 10 times through my neural network during training. Then my number of epochs is 10. There are cases, I'll get into that if we have time, while you might not run on every epoch that entire training data. Okay. So let's say, this simplicity is say you have 1,000 images and you're going to run one at a time, okay? But on every time you're only going to run, randomly choose 500. You can do that with steps. So steps just say how many batches out of that full data set I'm going to feed on an epoch. Okay, so that's that part. So another thing we get back into is the label encoding, okay? So again, if you remember, what's really coming in? You got apple, pear, peach, banana, but they're coming in, they don't come in as the word apple or pear or peach. They come in with an integer number that says what they are, okay? It's cardinal ordering, starting at 0. And what's outputted here isn't the name, but that number. So if this outputs 2, that means it's a peach. Okay, so let's talk a moment about label encoding. Okay, so one way is you could build your own label encoding. So if we went back to that earlier example, this would have been, I believe, both PIL and OpenCV, where I had a load directory. Okay, if you remember right, that function I wrote returned 2 things. It returned a list of my images, you know, 1 element per class of images, okay? And then a dictionary that mapped the class named cats, dogs, to its label value, 0 and 1. okay? But what I really need now, if I'm going to feed a neural network, if I give it 10 images, I have to give it 10 labels at the same time, okay? So I need to make a new list here for my data set that's basically parallels the labels, the images. But since data set in this example, entry 0 is cats, and then the next time around it's dogs, so I'm just going to create this new list, and I'm going to convert it to a NumPy array. Okay, so the number of elements in that list is going to be the current value coming through, the number of times I iterate. First time IX will be 0. So I'll have a list of labels that is exactly the same length as the list of images, okay? And they'll all be set to 0 for cats and then 1 for dogs. Okay, let's see what I got here. Okay, the final step is, again, we still don't, if we have a list of these different classes, when I put together a training set, I got to flatten it all out. So you can use the NumPy concat method, okay? And that's kind of like flattening. You'll take this one list, one element in this list, take the next one down, concatenate it to the end, take the next one down, concatenate it to the end, and basically flatten it out. And that's what this does. So now I'm ready. Okay, actually there's one more thing. One-hot encoding. If you're not familiar with it, you've probably heard about it and wonder, well, what does one-hot mean? Okay. Let's go back a few pictures. So, let's say this is your output, right? Okay. The output nodes have a cardinal ordering. So think of the top one as a 0, the next one's a 1, the next one's a 2, then a 3, then a 4, then a 5, okay? What you want to say, and then they have different signal strengths, okay? What you want to say is which one of those nodes is the right node. That's what I'm predicting, or the right answer, okay? So if it's class 3, it's node 3, right? So the way we do it is we just make this vector, it's 1D vector, that's the same length as the output layer, and we put a 1 in the position that corresponds to the node we want to output the right answer, and a 0 in all the other positions. And that's called one-hot encoding. Okay. So that's what I was talking about. So remember, an apple is a 0, so a one-hot encoding, let's say on a 4-node output layer, a 1 would be there, the pear, the 1 would be there, peach, the 1 would be there, banana, the 1 would be there. I'm going to skip how to do it in OpenCV just for brevity of time. In Keras, you can automatically do this. So you saw I created this list of labels that had the label number in it. They weren't one-hot encoded, so one entry said 3 for peach, one entry said 2 for pear, one said 0 for apple. I'm not going to turn those single scalar values in these one-hot encodings. Okay, so Keras has that built in a method called toCategorical. I can take that list, pass it to toCategorical, and it'll give me a one-hot encoded list. So it's just all in one. Don't have to write it yourself. Okay. So let's talk a little bit about data set splitting. Okay. So when you train a neural network, some of the data in your data set you have to hold aside that you don't use part of training. And that's called the test set or the holdout set. And the reason is we want some independent way to know whether our model works or not, okay? Because we could be training on our training data, get really high accuracy, but maybe we're getting high accuracy because we're overfitting to the data, okay? So we need some data it's never seen before, the holdout stuff, and we try that and see what we get, Okay, so the question is, so I got a data set, how much of the data do I need to set aside as test versus training? And it's really kind of a general rule of thumb. And it used to be a fixed number. Everybody said 20%. Okay, but what we've really found is the bigger and bigger data sets get, you don't need to maintain that proportion. You just need to have enough. So typically, if your data set is like 1,000 or less images, yeah, you need a fair amount to hold out to really to validate, the accuracy. But you get up to about 10,000 images or less, then only 10% is needed. And it looks like I got a typo there. It's supposed to be 1 million. Oh, no, greater than 10,000, excuse me. 5% is typically enough. But you still see in plenty of examples, people just keep doing the old 80-20 split. That's not what's done anymore. Okay. Did you?
So yeah, do you repeat the data that had the least amount of probability of being right? Meaning like the 5% that you add is the one that has like 50% less probability, or do you add like 97% being right, or do you add the 50% being right, probability being right, or you add the 20% being right? You know what I mean? So on the range of being between 3 and 97 of being the correct image,
Yeah.
right? 97 is like most of them are like right.
Right.
No.
You never retrain on the wrong stuff because you just fit onto those examples, right? So let's say I got my holdout set here, right?
Yeah.
Let's say 10% of the holdout set fails. And you say, well, let's take those 10% images and feed them back into training, right?
Yeah.
That seems like the smart thing to do. But you don't know if it'll just fit those because you don't got no new examples over here to test against. So your holdout set, no matter what the result is, never is put into the training. Okay. There is a technique where it's called train, validation, and test. That's 3 sets. And within there, a technique called cross-validation, where something kind of like that happens. Okay. But prior to splitting our data set, we also need to sort of randomly shuffle it. And the reason we need to do that is most times when you get a data set, whoever curated it kind of organized it in a nice manner, a neat manner. So the first batch of images are all label A, the next one all label B, the next one all label C. Nice sequential order. If I did an 80-20% split where I took the first 80% as training and the last 20% test, well, that last 20% is probably all one single label and doesn't represent the distribution of the data set, okay, and conversely the train. Okay, when the holdout set is supposed to have the same distribution of samples as your training, okay, and the simplest way to do that is just randomly shuffle the whole thing. Presumably, if the data set is big enough, okay, then any sampling I take anywhere in that data set of a large amount is going to have the same distribution of every other large amount of sample, okay. There is a case if your data set's kind of on the small side, and if we have time I can talk about it, where we do this pre-step on your data called stratification. Then we can do the random sampling or random shuffle. So we want to randomly shuffle it and then split. So if you were doing it by hand, not using a built-in method, just RumPy, with Python you can import random. You remember, you have your data set and your labels. Okay, so random numbers generators work on seeds. Okay, that is they're a pseudo-random generated. Okay. And a seed just says where in that sequence to start, okay? So if I went random.seed 101, it would start at a certain place, okay, in the pseudo-random number generation and generate random numbers, okay? And if I wanted that exact same sequence again, I would give it the same seed. Okay, so if I'm going to randomly shuffle my data set, I got to randomly shuffle the labels in the exact same random order. They all lined up. So this is showing is I just reissued the seed in front of the same seed in front of both of them. That guarantees me these two separate lists of exactly the same length get the exact same random shuffle. Okay. Okay, yeah, I kind of use a little different terminology here, data set and labels. Okay, so let's just assume here that my data is called X, my labels is called Y. It's been randomly shuffled. You know, the labels are in the right order as the images. And so I say, well, what's a really quick way to split this? Well, I just need to find a pivot point. Okay, and pivot point means everything to the left is training, everything to the right is test. So I just take the length of this array. Actually, it must be cut and paste. That should be X. Take the length of X, right, and then times it by the percent of my split. So if my split was 20% test, then that's going to be 0.8. So that's 0.8 times the length of this array. So 80% of the data is going to be on that side for train, and 20% is going to be on that side for test. So that's just array slicing in Python. So if you're not familiar with array slicing, you just look it up. It's a Python thing. Okay. But if you don't want to do it by hand, there's plenty of other ways to do it. This is probably the very last thing I ever use anymore out of scikit-learn. To me, it's just kind of an outdated package. But a lot of people like to use this train test split method in it. Okay, you give it your data set, you give it your labels, you say where you want to split it, what the percentage is. Shuffle defaults to true. You don't really need to say that. Who would not shuffle it, but whatever. And then it automatically returns everything pre-split for you in these nice 4 objects. You can also, the newer version of train test split handles stratification, which I kind of alluded to what you want to do if it's a smaller data set. Data set splitting in Keras can be done as part of the feeding, creating the data generator. So let's go back to here. I created a data generator, an image data generator. I'm telling to normalize the data. But I can also tell it to do a validation split. Now, this is not quite the same thing as test. Okay, what happens is, well, in this case, it would act like test. What this generator would do is it would take your data, randomly shuffle it, and hold 10% aside. Okay, and that 10% would never get used. But the way it would do it is, every time it ran an epoch, it would give the current accuracy from the training data. It would run the validation on a per epoch basis and show the current validation. Okay, and if there's time, I'll go into that more. But that's one way of doing it. And then here I'm just reading it again from a directory like cats and dogs, saying what the target size is, saying what the batch size is. There are multiple ways you can feed. You could feed the whole data set, or you could feed an image at a time, or a batch. The modern way is you feed it a batch at a time. Okay, and then every time I pass it through, the option whether I want, the next time I do it, do I want the same distribution of batches, or do I want a different distribution of batches? By setting shuffle to true, I've changed the distribution. And there are good reasons to always change your distribution. So and some of these things have arguments that are a little bit outdated. Meaning there's only one value we'd ever set it to anymore. Okay, so the next thing to talk about is image augmentation. And earlier I talked about when putting together a data collection having enough variance in it. to learn everything from spatial relationships to filtering out backgrounds to lighting conditions and so forth. But you may not necessarily have those pictures. For a number of things, you can actually create that picture through augmentation. You can take one of your existing pictures and do some modification to that picture that gives you that variance but doesn't stop that picture from being that object. Okay? So when we augment, create new pictures, the new picture is still that object. If you as a human being looked at that created picture, you would still see the same object. So here's a simple one. I zoom it. It's still the same object. So my apple was this big, now it's this big. Okay? I rotate it. Just kind of rotate it around. Still the same object, okay? I shift it left or right, okay? As long as it doesn't fall out, gets cropped outside of the image, it's still that object. So those are easy ones. Little ones that could be a little more iffy, but you keep them small, would be changing some of the coloring to emulate things being darker, like it's at night, or brighter, like the sun is right in front of you and saturating the picture. Okay. So, but you also have to be careful with image augmentation. When this started first getting popular, the first thing people did was just like full-blown augmentation, 100% on. And they deploy the model and you'd get weird results, okay? You don't really want to train your model for something it will never see. So let's say hypothetically it's for stop signs, but you'll never see an upside down stop sign. So why would you train it for an upside stop sign? Matter of fact, if you train it for that, it's probable that there's some scenario out there that's neither a stop sign or an actual upside down stop sign that it's still going to try to classify, and instead of saying not a class, it'll think the upside stop sign is the class, okay? And which will map to a stop sign. So only, the point here to make is, without going into the science behind it, know your environment, what it's actually going to see, only augment for the environmental conditions it's going to actually see. Don't turn everything on. Okay, so the easiest one to do is perspective change. This usually gives the biggest boost to both in accuracy and adaptability of your model, and that is changing your perspective. And those are done by flipping your image, 90 degrees, or horizontal flip, vertical flip, or rotating the image, or zooming in or out, or shifting the image back and forth in the picture. That helps it learn the spatial relationships of the various features that make up the object. Okay, so as a simple example, okay, here is original image here, and I'm going to do, that's what it would look like with a vertical flip, that's what it would look like in a horizontal flip. The nice thing is these are matrices, and the flips can be done with a matrix transpose operation, which is very efficient and fast, and it's just a shuffling of the pixels, so you don't have to deal with any interpolation of the pixel data. Nothing gets distorted. Here's just a little bit of code doing it with pill. So here I open the image, right? And in pill, the operation to do a vertical flip is called mirror, okay? Yeah, and to do a horizontal flip is called flip. But those would create the exact same images I just showed you. There's another way of doing it in pill. They have a sub-module called image ops in pill, okay? And actually, I guess it's the same thing, mirror or flip. Let me double check I didn't double a slide here. Oh, Yeah, I doubled up on the slide, I think. I'll fix that next time. Okay. I want to use OpenCV. Okay, you can see I read in the image. Okay, and it has a flip operation. And one of the arguments here is just on which axis to flip on. If I flip on 1, I'm flipping on the vertical axis. 0, I'm flipping on the horizontal axis. So really easy to do to make your own flipped images. Okay. Even NumPy has built-in matrix transpose. So, and sure enough, they call it the same. Flip and the same conventional. 1 is vertical, 0 is horizontal. Now you can make your own simple augmentation. Okay. So 90-degree rotations. So there's rotating 90, 180, 270. Okay. This operation is also very efficient. It can be done with a matrix transpose. It's different than a flip. Okay. And it also won't have any, it won't get clipped. So I'll just kind of quickly just show you. You can do it in pill, but again, in the handbook can show you the code in detail. We'll just move faster for brevity. In NumPy, it's a rote 90 method. But general.
That one, you are showing only 90 degrees, right?
Yeah.
It could be any angle.
Okay, that's a general rotation. Okay, and the reason I keep this separately is when you do these perfect 90-degree rotations, your image always maintains its dimensions. But the moment I do like 15, 65, 33, okay, you think about it, I'm a square rotating within another square. Part of my image is going to go out of image in the rotated version and get clipped. Okay, I think I show that. There's an example of what would happen if I took that apple within its original area, dimensions, and rotated it 45 degrees. This is what I'd get. So these parts would get clipped. Okay, so it's just precautionary, but I'll talk in a minute how you can handle that. Okay. Generally, you also want to limit the rotation to actually match the environment the model would be deployed in. Okay. So if in general you're in the real world in this deployment, for the most part, the image is always going to be dead on. I mean, there's always some variance, but to account for variance, but in general, dead on. Generally, plus or minus 15 degrees is enough of a rotation. Don't bother to do more, because now you're training it for things that we'll never see. Okay. If you're going up on an incline, generally minus 30 to 30 is enough. Start going 45, you're going to fall over anyways. Okay. But when you're talking about small objects, little spelling error. Okay, like a packages or money in that, in the real world, we see them from every possible angle. So that's the one in the case you would use the full range. Again, I covered the clip part here. Okay. So Adrian Rose-Rock, he's a really well-known guy in the OpenCV world. He's written lots of packages, routines around OpenCV. He's got this thing called image routines. A lot of people have used it, like to use his rotate_bound method of rotating, because he fixes the clipping. Okay, he figures out how much would get clipped in. He expands, he creates a larger region to rotate it in, and then resizes it, and it never gets clipped. Yeah, I'm just going to try to move a little bit quicker now. So here's an implementation of zooming in using pill. Okay. Actually, it's zooming out. How would you say it? No, that's zooming in. So you're expanding the picture within the same, okay? Because now you're, in a sense, making it larger. Instead of using anti-aliasing when you resize, you want to use bicubic. So that, in effect, gives you the best result when you're upsampling versus anti-aliasing when you're downsampling in PIL. OpenCV, it's the same algorithm, okay? But in this case, in using its terminology, when you're upsampling, you would use intercubic. Yeah, here's just a quick way to shift in NumPy. Generally, it's safe to shift images about up to plus or minus some random amount up to 10%. You're unlikely to lose the image, the object off of there, or even if it starts to go over the boundary, you're still going to have much of it there. But you get an ability to sort of shake that image around a little bit during training, help it learn that spatial relationships. You can do that with the roll method here, okay? And so, and you can roll, left or right or up or down. I'm just showing here. So the first argument is the image, okay? All right. The amount you want to shift by, here I'm just dividing it by 10, so that's 10%, and what axis. So axis 0 here, I'm shifting it up and down. Axis 1, I'm shifting it left and right. Okay. Again, if you shift too much, like 50%, you're pretty much going to guarantee to get a fractured image. Would you really want to put this into your neural network model? Yeah. So that's why I'm saying you don't want to go hog wild with image augmentation. People at first thought it was some kind of holy grail thing. There's limits. Okay. Here's an example of how you can deal with lighting. So in this case, I kind of make the light, I took that original Apple image and I made it appear as if the room is more dim. And I just simply use this routine in OpenCV called Convert, Scale, Absolute. And you just play around with the alpha and beta channel and you can get effects like that. Okay. If I wanted to do nighttime, here's a nighttime one. In this case, I specifically took the blue channel, darkened the blue channel, and I took the green and red and I reduced them. So I increased the blue and decreased green and red and gave myself something that emulated a nighttime version of that apple. Okay, so in Keras, some of this image augmentation I've showed you is, again, built into the image data generator. So the more old school people like me who want real fine-grained control will leap to OpenCV and do our own image augmentation. But, if you're just going into applied machine learning, just pull the, the levers and turn the knobs are already built into the framework. So I'll show you really quick how to do it in Keras. Okay, so in Keras, basically, let's see what we say here. Okay, you're going to read, here's an example. We're going to read in a single image. We're going to create a batch of just one image because image data generator works off of batches. So we're going to set augmentation options to vertically and horizontally flip it. And then we're going to use the flow method to create the batch. So let's have a quick look. I couldn't put the code on the same slide. Okay, so we go ahead and we read in that one image of an apple, right? And we're going to create image data generator, and we're going to initialize it to say we're going to randomly do horizontal flips and randomly do vertical flips. Then we're going to take that generator called the flow method, okay, which presumably we have some kind of batch here. It's only one image. We're faking a batch here for simplicity, but we're going to call it 6 times. And when we call it, basically, we're going to get a random sequence where sometimes it's that original apple, and sometimes it's going to be horizontally flipped, and sometimes it's going to be vertically flipped. Okay. Rotation is pretty much the same. I'll just show you the same sequence of code, but I just changed this argument to rotation 60. Okay. You know, the way it's going to be when you have just one augmentation here, it's going to be every other image it generates. So, you know, the first time around it'll be the original image. The next time around it'll be some randomly rotated version of it. Then back to the original image. The next time randomly rotated, and the range of rotation will be plus or minus 60 degrees. So it just did it for me. You don't have to write that code that I showed you. Only if you want to do something special. Here's the zoom range. So when you zoom out, when you zoom in. Okay, shifting when I showed you. So shifting on the width side or shifting on the height side, plus or minus 20%, up 2%. Remember, it'll be a random range between 0 and that %. Yeah.
It seems horribly inefficient to do all of this in the image domain. Why don't you instead do the convolution going from right to left instead of generating all of this data with images in different orientations?
I don't know.
You could do it in memory
Eh?
with your data already there.
Yeah, but possibly. Yeah, but it's just the way it's done. Done in the data sets. Similar with brightness, you can use the brightness range. This is basically the alpha beta channel. Okay, so you only get what you train for. Let me see what's on my slide here. Okay, so how do okay, so you want to get a good model, and like the sentence says here, you only get what you actually train for. So to increase performance of models, really you're looking at 4 things. I think we've discussed them all to some extent. Increasing the amount of time you train the model, increasing the depth of the model, adding regularization, that's that dropout, helps it more generalized, and expanding your data set where data augmentation. But in the end, no matter how much of these you do, the limitation, of course, will always be in the data set itself used to train the model. You know, if it's a lousy data set, I don't care what you do, it's still going to be a lousy model. Let me look at the time. See where we are. Oh, well, we'll talk a few more minutes and we'll wrap up. It's already like 4:35. Okay. So first, I just kind of want to talk about where the word model originates from. Okay, it actually comes from statistics, not AI. Okay, it's not really a new thing. So, before deep learning, okay, we used statistics to model things that weren't deterministic. And what I mean by deterministic in the relationship, that is, there was some kind of deterministic relationship between the inputs and outputs, okay? Therefore, like a linear relationship. When we went to more complex and there was a non-linear relationship, then we needed to model that non-linearity, you know. So let's take something real simple. Let's say age to income. You might think there's a linear relationship. You get older and you make more income, right? Okay. Well, you retire, and guess what? Your income goes down, right? That boom. We have the real world is that there are 2 linear relationships here. One that's for one time frame and a different linear relationship for another. And of course, the real world is many, many, many other factors really that would go into age equals income. So it's all broken up into non-linearity, okay? And so we try to write what was called models that would model that behavior. So that's where the term comes from. So it comes from classical statistics. Okay. And, okay. So now the word machine learning is kind of interesting where it comes from. It doesn't come from artificial intelligence either. Okay. It actually is a term that sort of caught on that when people were developing improved methods of doing linear regression and in logistic regression and card analysis, which is all we call now the classical machine learning, they tended to go to the UCI machine learning repository for data sets. They had all these curated data sets you could use to develop these algorithms with, okay, just say in the previous days. And that just happened to be the name University of California in Irvine called this group of data sets, and there the name stuck, machine learning. Okay. AI only got involved because of deep learning. Okay, so the other approach are all these statistical modelings. AI brought in neural networks. We've now fused both sides together and just call it machine learning. Okay. This is probably a good point to wrap up, but I'll tell you what, we'll spend just a few minutes if anybody has a question that I can hopefully answer. Okay.
Do barcodes create like a lot of trouble?
Do what?
Barcodes create a lot of trouble in machine learning. Have you encountered when people are building models that?
I don't know if barcodes are, well, one, reading barcodes has been well developed long before machine learning. Yeah. Okay, so that's not necessary for them. Are you talking about in the image is a barcode and the ability to recognize it? Well, there you would have to use, this is just image classification. There you would use object detection. So now I'll take my image and break it into particular regions and detect what's inside that region. And then based on what's inside that region, do some other processing. So I would train an object detecting a classifier to recognize where in the picture is a barcode. Then clip out the barcode and pass it into something that reads a barcode. I wouldn't train the neural network how to read the barcode. I trained how to recognize where the barcode is. Yeah?
Or finding the optimal epoch, like when you train basically a model, you just basically iterate through different epochs to see like
Okay, so you're talking about trying to find the best optima? Yeah. Yeah, that's when we didn't really get into it because we ran out of time, hyperparameter search. Okay. My advice when starting, before you learn this, is if you're doing image classification, start with the Atom Optimizer, and usually start sort of mid-level with a learning rate, probably 0.01. Pretty much anytime you go 0.1, it's going to be too high to learn. Okay, so what he's talking about here is you got to think of this learning as sort of kind of visualize it as a bunch of peaks and valleys. Okay, and you want to find the valley that's the deepest. Okay, that's like the one that's most accurate or has the least amount of loss. Okay, and when you find it, you want to dive down into it and get to the bottom of it, and that's called the global optima. Okay, how you set your learning rate and how your decay and how your optimizer you select, and even the initial random initialization on your weights can greatly affect whether you will actually find that, let's just call it that valley and drive down to it, or get stuck in another value that's good, but not as good, or get stuck on what's called a saddle point and you're going nowhere, or even the reverse, bounce all over, or even potentially diverge and actually be going in the opposite direction. So that's kind of one is kind of a science on its own, and two, fortunately, there are a number of tools coming out there that are making it easier and easier to find those values for you. I still do it by hand, the old-fashioned way. Oh, there you go, the dark over there. Okay, I didn't quite hear the whole question.
Yeah, sorry, I'm not talking very loud.
Okay, so she asked, is there a lower limit of images you should have before augmentation? Okay, it depends what you're doing. Okay, if you're training a model from scratch, you should, I don't care, even with image augmentation, should still start with 1,000 original images. Okay, I didn't go into if you're using transfer learning and you're transferring from a trained model that's in the same domain, starting with 100 images is shown to be generally pretty good.
If I'm going to build an image classifier, I've heard that using an existing previous model
Yeah.
and then ripping off like some of the last few layers is
Yeah.
a good strategy because it's kind of
Yeah, that's transfer learning.
Okay.
Okay, so just to be real brief on it, if what you want to classify is very similar to what this other model did, they're really close. Usually you only have to retrain the bottom, actually they use the reverse stuff, they call it the top. Where the outputs in models they call it the top. Where it inputs they call it the bottom. Okay, it's kind of counterintuitive. But you want to, generally you only have to retune the top part, and they refer to what they call the bottleneck layer. And the bottleneck layer is where you cross the threshold from the CNN front end to the DNN back end. And that's usually that flattening or global averaging layer. That's your bottleneck layer. Okay? So above the bottleneck layer, that is the DNN, that's what you retrain. Okay. The further you are away, then you might want to start training some of the other layers. Or retraining is what they would call it. All right, well, probably a good time to wrap it up. Sorry to keep you guys 15 minutes too long.
Are these slides available for us?
Okay, so let me go back to this very first page. See if we can get there fast. Probably should just quit presenting and just go to the first page. But oh, there it is. Okay, so that's the repo. In there you'll find the 3 handbooks that go with this, the code samples. The slides aren't there yet, but they'll be there tomorrow. So go into that repo, and then there's a subdirectory called ML4ALL. Everything will be there. Yeah. Thank you.